Hello there, and welcome to Sleepy Science Vault. Every object you have ever touched, every breath you have ever taken, every mountain, every ocean, every grain of sand, all of it is made of atoms. The chair beneath you, the air around you, the very body you inhabit right now. All of it, at its deepest level, is built from the same tiny, ancient building blocks that have existed since nearly the beginning of time. And when we say ancient, we mean it in a way that is almost impossible to hold in the mind. Many of the atoms that make up your body were not made here on Earth. They were forged inside stars, enormous, burning furnaces of nuclear fire that lived and died long before our sun even existed. When those stars reached the end of their lives, they did not simply go dark. Some of them exploded, in events so powerful, so luminous, that a single supernova can briefly outshine an entire galaxy of hundreds of billions of stars. And in that explosion, the atoms those stars had spent millions of years creating were scattered across the cosmos. Across the dark, silent space between worlds. Until, eventually, some of them drifted into the cloud of gas and dust that would become our solar system. That would become Earth. That would become you. You are, in a very literal sense, made of stardust. Not as a metaphor. As a fact of physics and chemistry and time. Now, of all the atoms in the visible universe, the vast majority belong to just two elements, hydrogen and helium. These are the oldest elements, the ones forged in the first few minutes after the Big Bang, when the universe was unimaginably hot and dense and new. Everything else, carbon, oxygen, iron, gold, nitrogen, calcium, all of it together makes up only a small fraction of the universe's total visible matter. We live in a universe that is, in its bones, almost entirely made of the two simplest things that exist. The simplest of all is hydrogen. One proton. One electron. Nothing else. It is the smallest atom, the lightest atom, and the most abundant atom in the known universe. A single hydrogen atom is so small that if you line them up side by side, you would need about 10 million of them just to stretch across the width of a human hair. And yet, for all its smallness, hydrogen is the foundation of almost everything. It fuels the stars. It combines with oxygen to make water. Without it, the chemistry of life would be impossible. At the other end of the natural scale sits uranium, the largest atom found in nature. Uranium has 92 protons packed into its nucleus, along with over 100 neutrons, and it is so large and so complex that it cannot quite hold itself together. It is radioactive, meaning it slowly sheds particles over time, releasing energy as it decays, gradually, over billions of years, transforming into lighter and lighter elements until it eventually becomes stable lead. Uranium exists at the very edge of what nature can sustain on its own. Now, here is something worth sitting with for a moment. Even in the stillest, most peaceful room, even in the deepest silence, matter is never truly at rest. Every atom around you is moving, vibrating. The atoms in the floor beneath you, the atoms in the walls, the atoms in your own skin, all of them are in constant, ceaseless motion. Temperature is, in a very real sense, just a measure of how fast those atoms are moving. Even when something feels perfectly still to the touch, at the atomic level it is alive with invisible activity. This truth was beautifully glimpsed in the early 19th century by a Scottish botanist named Robert Brown. In 1827, Brown was studying pollen grains suspended in water under a microscope, and he noticed something strange. The tiny particles inside the pollen were jittering, moving in small, random, unpredictable ways that never stopped. At first he thought perhaps the particles were alive in some way. But he soon found that even particles of dead matter did the same thing. He had no explanation. He simply observed it and documented it carefully. It would take nearly another century before Albert Einstein provided the mathematical explanation. Those particles were being pushed and nudged by the constant invisible motion of water molecules colliding with them from every direction. What Brown had seen was the visible fingerprint of atomic movement, the restless energy of matter expressing itself at a scale just barely large enough to observe. We call it Brownian motion now, and it remains one of the most quietly beautiful phenomena in all of science. To understand why atoms behave this way, why they move, why they react, why they bond, it helps to understand what an atom actually looks like on the inside. And the answer is surprising. At the center of every atom is a nucleus, an extraordinarily tiny, extraordinarily dense core made of protons and neutrons packed tightly together. Around that nucleus exists a cloud of electrons, moving in complex patterns through the surrounding space. But here's the part that changes how you see the world. The nucleus is almost unimaginably small compared to the total size of the atom. If you were to scale an atom up to the size of a large sports stadium, the nucleus would be roughly the size of a marble sitting at the center of the field. Everything else is empty space. The solid world around you, the table, the floor, your own hand, is almost entirely empty. What we experience as solidity is not atoms packed tightly together like bricks in a wall. It is the electromagnetic forces between electron clouds pushing back against each other, creating the sensation of resistance, of hardness, of touch. The physical world is, at its foundation, mostly nothing, held together by invisible forces. Within that nucleus, protons and neutrons do very different jobs. Protons carry a positive electrical charge. Electrons, orbiting in their cloud far from the nucleus, carry a negative charge, and it is the attraction between these opposite charges that holds the atom together. Neutrons carry no charge at all. They are electrically neutral, as their name suggests, and their primary role is to help stabilize the nucleus. Without neutrons, the positive protons packed tightly together would repel each other and the nucleus would fly apart. Of all these particles, protons hold a special significance. It is the number of protons in an atom's nucleus that defines what element that atom is. 1 proton, hydrogen. 2 protons, helium. 6 protons, carbon. 8 protons, oxygen. 79 protons, gold. Change the number of protons, and you have a completely different element. It is as fundamental as any rule in nature. The proton count is the atom's identity. But neutrons can vary. 2 atoms can have the same number of protons, making them the same element, while having different numbers of neutrons in their nuclei. We call these variations isotopes. Carbon, for example, almost always has 6 neutrons alongside its 6 protons. But a small fraction of carbon atoms have 7 neutrons, or 8. They are still carbon. They still behave like carbon in most ways. But their nuclei are slightly different, slightly heavier. Some isotopes are stable and can exist indefinitely. Others are unstable and will eventually decay, releasing energy as they shift toward a more stable form. Radioactive isotopes, in particular, have become some of the most useful tools in medicine, archaeology, and energy generation, all because of this small variation in the number of neutrons an atom carries. The world of atoms is quiet. It is invisible to us in our daily lives. And yet everything, every experience, every texture, every color, every scent, is built upon it. Beneath the surface of ordinary reality lies this extraordinary architecture of particles and forces and empty space, humming with invisible motion, carrying within it the memory of ancient stars. The atoms in your body have been part of this universe for billions of years. They have traveled further than we can imagine, through processes more dramatic than we can fully picture. And here they are now, assembled, for this brief moment in time, into you. It is worth pausing, just for a moment, on something we touched on at the end of our last journey, isotopes. Because while the concept seems technical at first glance, there is something quietly wonderful hidden inside it. Take carbon. Carbon always has 6 protons. That is what makes it carbon, and nothing about that ever changes. But the number of neutrons in a carbon nucleus can vary. The most common form, carbon-12, carries 6 neutrons alongside its 6 protons. A rarer form, carbon-14, carries 8. Both are carbon. Both behave like carbon in chemistry and in life. But carbon-14 has an unstable nucleus, and over thousands of years, it slowly decays, shedding particles, releasing energy, transforming gradually into nitrogen. And because it decays at a known, steady, predictable rate, scientists can measure how much carbon-14 remains in an ancient object, a piece of wood, a fragment of bone, a scrap of cloth, and calculate, with remarkable precision, how long ago that object was once alive. A technique called radiocarbon dating. The invisible architecture of the atom, revealing the deep past. And isotopes reveal something else, too, something about the nature of energy itself at the atomic scale. When the nucleus of an atom absorbs or releases energy, it does not do so in a smooth, continuous flow. It does so in precise, specific amounts, what physicists call quanta. Discrete packets of energy, like steps on a staircase rather than a slope you can slide down freely. The same is true of the electrons surrounding a nucleus. When an electron absorbs energy, it jumps to a higher energy level. When it releases that energy, it drops back down, and the energy it releases comes out as light, at a very specific wavelength. Each element has its own unique set of these energy levels, its own fingerprint of light. When scientists pass that light through a prism, they see a pattern of distinct colored lines, unique to that element, like a barcode written in color. This is called an atomic spectrum, and it is one of the most powerful tools we have for understanding what the universe is made of. Astronomers can point a telescope at a star 1,000 light-years away and, by analyzing the light, tell you exactly which elements are burning inside it. The atom, it turns out, speaks in light. And once you know how to listen, it tells you everything. But now we need to go deeper. Because the story of the atom does not end with protons, neutrons, and electrons. The proton and the neutron, which for decades were considered the fundamental building blocks of the nucleus, are not actually fundamental at all. They are themselves made of something smaller. Inside every proton and every neutron are particles called quarks. They are extraordinary things, never found alone in nature, always bound together in combinations by one of the most powerful forces in the universe. A proton is made of 3 quarks, 2 of a type called up and 1 called down. A neutron is also made of 3 quarks, but arranged differently, 2 down quarks and 1 up. These names, up and down, are not descriptions of direction. They are simply labels physicists gave to different varieties of quark, properties that describe how they behave and interact. The universe does not always lend itself to intuitive naming. What holds these quarks together inside the proton and neutron is a force called the strong nuclear force, carried by particles called gluons. And this force is, by a significant margin, the strongest force in nature. It has to be. The protons in an atomic nucleus are all positively charged, and positive charges repel each other powerfully. The only reason a nucleus does not immediately explode is because the strong nuclear force, operating at extremely short range, overpowers that repulsion and binds everything together. It is a force of extraordinary intensity, acting over distances almost incomprehensibly small. Quarks and electrons sit at what we currently believe is the deepest level of matter, what physicists call elementary particles. Unlike protons and neutrons, they have no known internal structure. As far as our best instruments and our best theories can determine, they are not made of anything smaller. They simply are. The framework that organizes these particles and the forces between them is called the Standard Model of Particle Physics, and it is one of the most tested, most precisely confirmed theories in all of science. It is not complete, physicists are the first to say so, but within its domain, it describes the subatomic world with extraordinary accuracy. Now, the subatomic world is populated by far more than just quarks and electrons. Nature, it turns out, is enormously creative at these tiny scales. There are many other particles, some familiar, some deeply strange, and most of them do not last long. Many subatomic particles are unstable. They are born, they exist for a fraction of a second, sometimes a fraction of a microsecond, sometimes even less, and then they decay, transforming into other particles, shedding energy as they go. Their lifetimes are so brief that they can only be observed indirectly, in the aftermath of collisions inside enormous machines called particle accelerators. These accelerators, the most famous of which is the Large Hadron Collider near Geneva, Switzerland, work by taking particles and accelerating them to velocities approaching the speed of light, then steering them into head-on collisions. The energy released in those collisions is so intense that it briefly recreates conditions similar to those of the very early universe, just fractions of a second after the Big Bang. And in that concentrated burst of energy, new particles are born. They flicker into existence for an instant, leave their signatures in the detectors surrounding the collision point, and then vanish. Scientists piece together what happened from the trails they leave behind, like reading the story of a firework from the shape of the sparks. What makes this process even more remarkable is something that sits at the heart of Einstein's most famous insight, that energy and mass are interchangeable. The equation E equals mc squared tells us that mass is, in essence, concentrated energy, and that energy, under the right conditions, can become mass. In particle accelerators, this is not just theory. It is something that happens, routinely, every time a collision is energetic enough. Energy converts directly into matter, specifically, into pairs of particles. And not just any pairs. Nature has a rule: when energy creates matter this way, it always creates a particle and its antimatter counterpart simultaneously. A particle-antiparticle pair, born together from pure energy. Antimatter is one of the more astonishing features of the universe. Every particle of ordinary matter has a corresponding antiparticle, identical in mass, but opposite in charge and certain other properties. The antiparticle of the electron is called the positron. The antiparticle of the proton is the antiproton. They are mirror images, in a sense, and they cannot coexist with their matter counterparts for long. When a particle meets its antiparticle, both are instantly annihilated. They do not simply collide and bounce away. They vanish, converting entirely back into energy, released as a burst of high-energy light called gamma rays. Every last bit of their mass becomes energy, with perfect efficiency. It is the most complete conversion of matter into energy that nature allows. This raises a question that physicists find genuinely troubling: if matter and antimatter are always created in equal amounts, and if they annihilate each other on contact, then why does the universe contain anything at all? At the moment of the Big Bang, matter and antimatter should have been produced in equal quantities, and they should have destroyed each other completely, leaving nothing but energy. And yet, here we are. Galaxies, stars, planets, life. Something tipped the balance, ever so slightly, in favor of matter. For every billion antiparticles produced in the early universe, there were 1,000,000,001 particles of ordinary matter. One extra. And when the Great Annihilation was over, those 1 in a billion survivors were all that remained. All the matter in the observable universe, every star, every atom in your body, is the remnant of that tiny asymmetry. Scientists have a name for this puzzle: baryon asymmetry. And they do not yet have a complete explanation for it. The universe, it seems, should not quite exist. And yet here it is. Now, everything we have described, quarks, electrons, antiparticles, energy converting into matter, all of it operates according to a set of rules so different from everyday experience that they require an entirely new framework to understand. That framework is quantum mechanics. It is the physics of the very small. And it is, by nearly any measure, the most successful physical theory ever devised. Its predictions have been tested to extraordinary precision, again and again, and it has never been found wrong within its domain. It underlies the technology in your phone, in medical scanners, in lasers, in the materials that make modern electronics possible. And yet, for all its predictive power, quantum mechanics describes a world that operates in ways that feel fundamentally strange to a mind built for the everyday scale of things. At the quantum level, particles do not follow neat, predictable paths the way a thrown ball does. Their behavior is governed not by certainty, but by probability. A particle does not have a definite position until it is measured. It exists, in a sense, in a spread of possible states simultaneously, and only when observed does it resolve into one specific outcome. The act of measurement itself is not passive. It participates in the result. This is not a limitation of our instruments. It is not that the particle has a definite position and we simply cannot measure it precisely enough. According to quantum mechanics, the uncertainty is real. It is built into the fabric of nature at this scale. The universe, at its deepest level, does not deal in certainties. It deals in probabilities, in tendencies, in the language of waves and superposition and the strange mathematics of states that have not yet resolved. It is a world that operates by its own quiet logic, a logic that does not ask permission from our intuitions, and does not particularly care whether we find it comfortable. And somehow, from this invisible foundation of uncertainty and probability in particle pairs flickering in and out of existence, from quarks bound together by forces of almost unimaginable strength, from electrons existing in clouds of probable position, from energy that can become matter and matter that can become energy, from all of this, the solid, familiar, tangible world emerges. The world you can touch and smell and see. The world of mountains and oceans and late-night quiet. Beneath every moment of stillness, beneath every ordinary thing, the quantum world continues, restless, precise, and endlessly strange. There is a question that seems simple on the surface, and yet pulled at the minds of the greatest physicists of the 20th century for decades. It is this: what is a particle, really? When we imagine an electron, or a photon of light, most of us picture something like a tiny sphere, a miniature ball, hurtling through space along a definite path. It seems like a reasonable picture. It matches how we experience the larger world. A thrown stone follows a path. A rolling marble has a position. Surely a particle does too. But nature, at the quantum scale, does not cooperate with this picture. And one of the first and most unsettling discoveries of quantum physics was that particles, electrons, photons, even atoms, do not behave like tiny balls at all. They behave, under the right conditions, like waves. This is called wave-particle duality, and it is one of those ideas that sounds like a riddle but is, in fact, a precise and experimentally confirmed feature of reality. The same electron that registers as a single point of impact on a detector, like a particle hitting a target, will, when allowed to travel through two openings simultaneously, create an interference pattern on the other side, as though it passed through both openings at once and interfered with itself. Like a wave on water passing through two gaps and creating rippling rings that cross and amplify and cancel each other out. This experiment, known as the double-slit experiment, has been called the most beautiful experiment in physics. It has been repeated in countless variations, with electrons, with photons, with whole atoms, and even with molecules far larger than atoms. The result is always the same. When you are not watching which path the particle takes, it behaves like a wave and produces an interference pattern. When you watch, when you place a detector to observe which opening the particle passes through, the interference pattern disappears. The particle, somehow, behaves differently when it is being observed. This is not a malfunction of the experiment. It is not an artifact of the detector disturbing the particle in some simple mechanical way. It is something far stranger. The act of gaining information about the particle, the act of measurement itself, changes the outcome. Nature seems to respond differently when it is being watched. And while that sentence sounds almost mystical, it is simply what the mathematics of quantum mechanics predicts, and what experiment after experiment confirms. The reason lies in one of the central features of quantum theory, superposition. Before measurement, a quantum particle does not have a single definite state. It exists in a combination, a superposition, of multiple possible states simultaneously. An electron does not have a definite position. It has a range of probable positions, described by a mathematical wave function that tells you how likely you are to find it at any given location if you look. Only when a measurement is made does that spread of possibilities collapse into a single, definite outcome. And crucially, which outcome occurs cannot be predicted with certainty in advance. Only the probability of each possible outcome can be calculated. This is not a temporary limitation. It is not that the universe knows the answer in advance and is simply keeping it from us. According to quantum mechanics, the universe genuinely has not decided until the moment of measurement. The moon, as the physicist John Wheeler once put it in a slightly different context, is not there when no one is looking. At least, not in the precise, definite way we tend to assume. Classical physics, the physics of Newton, of planets and pendulums and falling apples, describes a deterministic universe. Given the exact position and velocity of every particle, classical physics could, in principle, predict the future with perfect precision. Quantum mechanics dismantled this picture entirely. At the deepest level, nature is irreducibly probabilistic. Randomness is not a feature we introduce because we lack information. It is woven into the structure of things. For many physicists, including, famously, Einstein himself, this was deeply uncomfortable. Einstein never fully accepted the probabilistic interpretation of quantum mechanics. He believed, until the end of his life, that the randomness was a sign that the theory was incomplete, that there were hidden variables underneath, a deeper layer of reality that, once understood, would restore determinism to physics. He expressed his discomfort in one of the most quoted phrases in all of science, that he could not believe God plays dice with the universe. But the dice, it seems, are real. Subsequent experiments, particularly those designed to test a set of inequalities developed by physicist John Bell in the 1960s, have shown, with extraordinary statistical confidence, that the randomness of quantum mechanics cannot be explained by any hidden classical variables operating beneath the surface. The universe, at this level, truly is probabilistic. And that is simply what it is. Now, if superposition already stretches our intuitions considerably, what comes next stretches them further still. Because quantum mechanics permits something that, even by the standards of the subatomic world, seems genuinely extraordinary. It is called entanglement. When two particles interact in certain ways, they can become entangled, linked in a way that persists even after they are separated by vast distances. Once entangled, the quantum state of each particle cannot be described independently of the other. They form, in a sense, a single system, no matter how far apart they are. And when a measurement is made on one particle, determining its state, the entangled partner instantaneously reflects a correlated outcome. Measure the spin of one entangled electron and find it pointing upward, and its partner, perhaps on the other side of the planet, or the other side of a room, will be found pointing downward. Every time. Not because a signal traveled between them. Not because one particle somehow sent information to the other. But because they were never truly separate to begin with. Einstein found this deeply troubling. He called it spooky action at a distance, and he used it as an argument that quantum mechanics must be incomplete, because surely nothing could influence something else instantaneously across space without some kind of physical connection. But again, experiment has sided with the theory rather than with Einstein's discomfort. Entanglement is real. It has been demonstrated over distances of hundreds of kilometers, between particles separated by fiber optic cables spanning entire cities, and even between ground stations and satellites in orbit. The correlations appear, reliably, instantaneously, regardless of distance. What entanglement does not do is transmit usable information faster than light. The outcome of a measurement on one particle is random. You cannot control it, and therefore cannot encode a message in it. The correlation only becomes apparent when the results from both particles are compared, which requires a classical channel of communication, limited by the speed of light. So relativity is not violated. But entanglement remains one of the most philosophically unsettling features of quantum physics, a reminder that our intuitions about separateness, about objects being distinct and independent things located in definite places, may not accurately reflect the underlying reality of the universe. There is another quantum phenomenon that deserves its own moment of quiet astonishment, and it is called tunneling. In the classical world, the world of everyday physics, if a ball is rolling along the ground and encounters a hill, and it does not have enough energy to climb that hill, it simply stops. It cannot pass through the hill. The barrier is real, the energy is insufficient, and that is the end of the story. But in the quantum world, this logic does not hold. Because a quantum particle does not have a perfectly definite position, it has a wave function, a spread of probable locations. There is always a small but non-zero probability that the particle will be found on the other side of the barrier, even without the energy to classically surmount it. It does not go over. It does not go around. It appears, with some probability, on the other side, as though the barrier were not entirely there. As though it had passed through. This is quantum tunneling, and it is not a theoretical curiosity. It is a foundational process in the physical world. Nuclear fusion in the Sun depends on it. Protons inside the Sun do not have enough thermal energy to overcome their mutual electromagnetic repulsion and fuse together, but they tunnel through the barrier that repulsion creates, and in doing so, power the fusion reactions that make the Sun shine. Without quantum tunneling, the Sun would not produce light. Stars would not burn. The conditions for life on Earth would not exist. Tunneling is also the principle behind the scanning tunneling microscope, an instrument so sensitive that it can image individual atoms on a surface by measuring the quantum tunneling of electrons across a tiny gap. And it plays a role in certain chemical reactions in biology, including processes inside our own cells. The quantum world, strange and counterintuitive as it is, reaches up into the scale of life in chemistry and starlight. And it reaches even into what we think of as empty space. Because in quantum mechanics, there is no such thing as truly empty space. Even a perfect vacuum, or region of space with no particles, no light, no anything, is not truly empty. It seethes with what physicists call virtual particles, pairs of particles and antiparticles that flicker into existence spontaneously, exist for an extraordinarily brief moment, and then annihilate each other and vanish. They are permitted by the Heisenberg uncertainty principle, one of the foundational principles of quantum mechanics, which allows brief violations of energy conservation, provided they occur over short enough timescales. The shorter the duration, the larger the energy fluctuation permitted. These virtual particles are not directly observable in the conventional sense. By definition, they disappear before they can be measured as real particles. But their effects are measurable. The Casimir effect, a tiny but real attractive force between two uncharged metal plates placed very close together in a vacuum, is a consequence of virtual particle activity. The plates restrict which virtual particles can exist in the space between them, creating a slight imbalance in pressure compared to the space outside, and the plates are pushed together by an amount that has been measured and confirmed experimentally. The vacuum pushes back. The emptiness is alive with quantum activity. There is a state of matter, rarely observed, requiring temperatures close to absolute zero, where quantum effects become visible not at the subatomic scale but at the scale of bulk materials. It is called superfluidity. Certain substances, most famously helium-4 cooled to within a fraction of a degree of absolute zero, enter a phase in which they flow with absolutely zero resistance. Not very little resistance. Zero. A superfluid, if set in motion, will continue to flow forever, climbing up the walls of its container, flowing through openings too small for classical fluids to pass through, behaving in ways that seem to defy every intuition about how liquids work. What makes this possible is that at such extreme temperatures, the quantum wave functions of the individual atoms begin to overlap and merge. The atoms lose their individual quantum identities and begin behaving as a single coherent quantum entity, a collective state governed by one shared wave function. The randomness and disorder that normally produces friction and resistance simply vanishes. The superfluid moves as one. It is quantum mechanics operating at a scale you can see, touch, and, in a sense, watch in real time, if you have the right equipment and the extraordinary cold required to create it. These phenomena, superposition, entanglement, tunneling, virtual particles, superfluidity, are not separate curiosities. They are all expressions of the same underlying quantum reality. A reality that operates by its own rules, indifferent to our expectations, astonishing in its precision, and stranger than almost anything we could have invented. And now, from the strange heart of quantum mechanics, we turn to something that brings all of this into a different kind of focus. Something that travels through the quantum world with almost no interaction at all, threading through matter as though matter were barely there. These are particles that pass through you, through the Earth, through entire stars, with almost nothing to slow them down or turn them aside. They are called neutrinos. And right now, as you listen to this, they are passing through you. Not a few of them. Not a trickle. Trillions of neutrinos pass through your body every single second. Through every square centimeter of you, from the top of your head to the soles of your feet, a vast, invisible stream of particles is flowing, continuously, at nearly the speed of light. They come primarily from the sun, produced in the nuclear fusion reactions burning at its core. They travel the 93 million miles between the sun and the Earth in about 8 minutes, passing through the entire body of the Earth as easily as you might pass your hand through fog, and continue outward into space beyond. They are often called ghost particles, and the name is apartment. Neutrinos interact with matter only through the weak nuclear force, one of the 4 fundamental forces of nature, and through gravity. They do not respond to electromagnetism, which means they cannot be blocked by ordinary material the way photons and charged particles can. To a neutrino, a wall is not an obstacle. A building is not an obstacle. The entire planet Earth is barely an obstacle. A neutrino traveling straight through the Earth from one side to the other has only a tiny probability of interacting with anything along the way. If you wanted to stop half of all incoming solar neutrinos, you would need a wall of lead approximately 1 light-year thick. And yet neutrinos are everywhere. They are among the most abundant particles in the universe. Produced in nuclear reactions in stars, in supernovae, in the decay of radioactive elements, and in the first moments after the Big Bang, the universe is absolutely saturated with them. There are estimated to be hundreds of millions of relic neutrinos from the Big Bang in every cubic centimeter of space, left over from the first second of the universe's existence. They have been streaming through space ever since, barely interacting with anything, carrying within them a kind of fossil record of the very earliest moments of time. For a long time, physicists believed neutrinos were massless, moving at exactly the speed of light, like photons. But experiments in the late 1990s revealed something unexpected: neutrinos oscillate. They change from one type to another as they travel, a quantum mechanical phenomenon that is only possible if they have a small but non-zero mass. This discovery was significant enough to earn its investigators the Nobel Prize in Physics in 2015. Neutrinos have mass. Not much. They are among the lightest massive particles known, but enough to tell us that the Standard Model, as it stood, was incomplete. Something was missing. That discovery quietly shifted our understanding of particle physics. It suggested that there are aspects of the neutrino's nature, perhaps even of the nature of mass itself, that we do not yet fully understand. Neutrinos remain one of the most actively studied particles in physics, and some of the experiments designed to detect and study them are among the most remarkable scientific instruments ever built. The IceCube Neutrino Observatory, for instance, is buried deep in the ice sheet at the South Pole. It consists of thousands of sensitive light detectors arranged in a cubic kilometer of Antarctic ice, one of the most transparent natural materials on Earth. When a neutrino, passing through the Earth, very occasionally interacts with an atom in the ice, it produces a faint flash of blue light called Cherenkov radiation. IceCube watches for these flashes in the dark, frozen quiet beneath the polar ice, catching, on average, a handful of high-energy neutrino events per year from sources far outside our solar system. From the hearts of distant galaxies. From cosmic events of almost inconceivable power. There are other neutrino detectors built deep underground, inside old mines, beneath mountains, where the rock above shields the detectors from other cosmic ray particles, leaving the neutrinos, which pass through rock as freely as through air, as the primary signal. The Sudbury Neutrino Observatory in Canada, the Super Kamiokande detector in Japan, a vast tank filled with 50,000 tons of ultrapure water, watched by thousands of light sensors. These are the instruments through which we have learned most of what we know about neutrinos. And what we know, even now, remains incomplete. The neutrino is thought to have a tiny mass, but that mass has not been precisely measured. It is possible that neutrinos are what physicists call majorana particles, meaning that they are their own antiparticles. If that is true, there are profound implications for our understanding of why the universe contains more matter than antimatter. Neutrinos may hold part of the answer to one of the deepest puzzles in cosmology: why anything exists at all. So here is this remarkable situation. One of the most common particles in the universe, a particle present in unimaginable numbers, flooding through space in every direction, passing through planets and stars and the bodies of living creatures without pause, remains one of the least understood. The universe is speaking to us in neutrinos, continuously, in vast quantities. And we are only just beginning to learn to listen. Right now, trillions of them are moving through you. Not disturbing a single atom. Not leaving any trace. Not slowing down for a moment. Carrying information about nuclear fires burning 93 million miles away, or supernova explosions in distant galaxies, or the first blazing second of the universe's existence, all of it streaming through you in the quiet of this moment, as gently and completely as if you were not there at all. There is something strangely humbling about that. And something beautiful in it too. Among the quietest revolutions in modern physics, quiet in the sense that it happened not with a dramatic announcement, but through years of patient, painstaking observation deep underground, was the discovery that neutrinos are not what we thought they were. For much of the 20th century, the neutrino was assumed to be massless. It was a particle that interacted with almost nothing, traveled at or near the speed of light, and existed in three distinct varieties, three flavors, as physicists call them. There is the electron neutrino, the muon neutrino, and the tau neutrino. Each is associated with a corresponding charged particle, the electron, and its heavier cousins the muon and the tau. These pairings are not arbitrary, they reflect deep symmetries in the structure of matter, relationships encoded in the mathematics of the Standard Model. Each flavor of neutrino is produced in specific types of interactions and, under the original theory, was expected to remain that flavor forever. Nature had other ideas. The first hints came from the sun. Physicists had calculated, with considerable precision, how many electron neutrinos the sun should be producing through its nuclear fusion reactions. They built detectors. They waited. And when they counted the electron neutrinos actually arriving at Earth, they found roughly a third of the expected number. For years this was known as the solar neutrino problem, and it generated genuine uncertainty. Were the solar models wrong? Were the detectors flawed? Was the theory of nuclear fusion missing something? The answer, when it finally came, was none of those things. The neutrinos were there. All of them. But by the time they arrived at Earth, having traveled 93 million miles through space over the course of about 8 minutes, many of them were no longer electron neutrinos. They had changed. They had transformed, in transit, into muon neutrinos and tau neutrinos, flavors that the early detectors were not sensitive to, and so were not counted. The neutrinos were oscillating, shifting from one identity to another as they traveled, cycling through their 3 flavors in a quantum mechanical process that has no real parallel in everyday experience. This phenomenon, neutrino oscillation, is one of the more elegant demonstrations of quantum mechanics operating at a large scale. It works because each of the 3 neutrino flavors is not actually a single quantum state of definite mass. Each flavor is a mixture, a quantum superposition, of 3 underlying mass states. And because those mass states have slightly different masses, they travel through space at slightly different rates, even when moving at nearly the speed of light. Over time, the interference between these mass states causes the neutrino's flavor identity to cycle. An electron neutrino produced in the sun's core gradually becomes a mixture of all 3 flavors by the time it reaches Earth. Measure it, and you might find it in any of the 3 states, with probabilities that depend on how far it has traveled and the specific mass differences involved. The experimental confirmation of this came most definitively from the Sudbury Neutrino Observatory in Canada, in results published in 2001 and 2002. For the first time, physicists built a detector sensitive to all 3 neutrino flavors simultaneously, using heavy water in which the hydrogen atoms contain an extra neutron in their nuclei. When the total flux of all neutrino flavors was measured, it matched the solar models perfectly. The neutrinos were all there. They had simply changed along the way. The solar neutrino problem was not a problem with the sun. It was a window into something new about the neutrino itself. And what that window revealed had consequences that reached well beyond the neutrino. Because neutrino oscillation is only possible if the different mass states have different masses. And different masses means the neutrinos cannot be massless. Neutrinos have mass. Small, extraordinarily small, less than a millionth of the mass of an electron, but real. Non-zero. And that fact, seemingly minor, was enough to crack open the framework that had organized particle physics for decades. The Standard Model, as it was originally formulated, predicted that neutrinos were massless. It was built on that assumption. The discovery of neutrino oscillation showed that assumption was wrong, that the model, for all its extraordinary success and precision, was incomplete. Something was missing. Some piece of the deeper theory had not yet been found. The Standard Model remained, and remains today, the most precisely tested theory in physics. But neutrino oscillation placed a flag at its boundary and said, "Here's where we go beyond it." The physicists who led the experimental work confirming neutrino oscillation, Takaaki Kajita of Japan, working with the Super Kamiokande detector, and Arthur MacDonald of Canada, working with the Sudbury Observatory, were awarded the Nobel Prize in Physics in 2015. A recognition of one of the most consequential discoveries in particle physics of the past half-century. But to fully appreciate what neutrino oscillation revealed, and what remains to be understood, it helps to step back and look at the larger architecture that the Standard Model provides, the framework into which neutrinos, quarks, electrons, and all the other known particles fit. The Standard Model is, at its core, a classification system. A periodic table, in a sense, but for the fundamental constituents of the universe. It organizes everything we know about elementary particles and the forces between them into a single coherent structure, a structure built on deep mathematical symmetries that constrain what kinds of particles can exist and how they must interact. At the broadest level, the Standard Model divides particles into two categories: matter particles and force carriers. Matter particles are the ones that make up the physical substance of the universe, the quarks that combine to form protons and neutrons, and the leptons, which include electrons and neutrinos. Force carriers are a different kind of particle entirely. They are the particles through which forces are transmitted. When two electrons repel each other, they do so by exchanging photons, the carriers of the electromagnetic force. When quarks are bound together inside a proton, they exchange particles called gluons, the carriers of the strong nuclear force. The weak nuclear force has its own carriers, called the W and Z bosons, responsible for processes like radioactive beta decay. Each force has its messenger. Matter particles come in two types: quarks, which feel the strong nuclear force and make up the particles inside atomic nuclei, and leptons, which do not feel the strong force and include the electron and its heavier relatives along with their associated neutrinos. Both quarks and leptons come in three generations, three sets of particles that are structurally identical except for mass. The first generation contains the lightest particles, up and down quarks, the electron, and the electron neutrino. The second generation contains heavier versions, charm and strange quarks, the muon, and the muon neutrino. The third generation is heavier still, top and bottom quarks, the tau particle, and the tau neutrino. Why three generations? Why not 1, or 5, or 10? That is a question the Standard Model cannot answer. It describes the three generations with great precision. It does not explain why there are exactly three. It is one of the open questions at the heart of physics, one of those places where the theory is silent, and silence in physics usually means there is something deeper waiting to be found. The particles of the Standard Model, all of them, quarks and leptons and force carriers together, are considered elementary. They have no known internal structure. They are not made of smaller pieces, at least not at any scale our instruments can currently probe. And among them, the ones most central to the matter we encounter in everyday life are the up quark, the down quark, and the electron. Almost everything in your body, in the room around you, in the visible universe, is built from these three particles interacting through the forces the Standard Model describes. The rest of the particles the muons and tau particles, the strange and charm quarks, the heavy bosons, these are the particles of extreme conditions, produced in cosmic ray showers, in the interiors of collapsing stars, in the first fraction of a second after the Big Bang, and in the controlled energetic collisions of particle accelerators. Which brings us to those extraordinary machines. The Large Hadron Collider at CERN, the European Organization for Nuclear Research, is, by many measures, the most complex scientific instrument ever built. It sits in a circular tunnel approximately 27 kilometers in circumference, buried about 100 meters beneath the border between France and Switzerland near the city of Geneva. Inside that tunnel, two beams of protons travel in opposite directions, accelerated by superconducting magnets cooled to temperatures colder than outer space, reaching velocities so close to the speed of light that the difference becomes almost meaningless to state. Each proton in those beams carries an energy that dwarfs what any previous accelerator achieved. And at designated collision points, the beams are steered into each other. What happens in those collisions is, in a sense, the closest thing to time travel that physics currently offers. The energy density at the moment of collision is so extreme, concentrated into such a tiny region of space, that it briefly recreates conditions similar to those that existed in the universe when it was less than a trillionth of a second old. Particles that have not existed freely since the first moments after the Big Bang flicker into existence, travel tiny distances, and decay. The detectors surrounding the collision points, some of them the size of large buildings, built from millions of individual sensor components, capture every trace, every trail, every signal left by those fleeting particles, and record it all for analysis. It was at the LHC, in 2012, that the Higgs boson was finally discovered. The Higgs had been predicted by the Standard Model since 1964, a necessary particle, one whose existence was implied by the mathematics of the theory, but it had never been directly observed. It was the last missing piece of the Standard Model's particle content, and finding it confirmed that the theoretical framework physicists had built over decades was not merely a useful approximation, but a genuine description of something real. The discovery was announced to extraordinary celebration in the physics community, and the Nobel Prize followed within a year, awarded to Peter Higgs and François Englert, whose theoretical work had predicted the particle nearly half a century earlier. The Higgs boson matters because it is connected to a field that permeates all of space, the Higgs field, and it is through interaction with this field that many particles acquire mass. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly are light. Photons, which do not interact with the Higgs field at all, are massless and travel at the speed of light. It is an elegant mechanism, a way of explaining why different particles have such different masses, rooted in symmetry and field theory, and its experimental confirmation was one of the great triumphs of 20th and 21st century physics. But the LHC did not only find the Higgs. It has produced enormous amounts of data on quark behavior, on the properties of known particles measured with greater precision than ever before, on the interactions of forces at energies never previously accessible. Each collision is, in a small but real sense, a window into the conditions of the early universe, a brief recreation of moments that occurred nearly 14 billion years ago, lasting for a tiny fraction of a second before ordinary physics reasserts itself and the exotic particles decay into more stable forms. Physicists analyze those decay signatures, the trails of particles left in the detector, the way a forensic investigator might reconstruct an event from its aftermath. The original particles are long gone by the time any measurement is made. What remains is the evidence, and from that evidence, the original event is inferred. It is painstaking, statistical, deeply mathematical work, and it has revealed a great deal about the structure of matter and the behavior of forces at the smallest scales we can currently reach. And yet, for all the LHC has confirmed, it has also reinforced a growing sense that the Standard Model, impressive as it is not the final word. There are phenomena the Standard Model does not explain. Dark matter, the invisible mass that makes up roughly a quarter of the universe's total energy content, has no candidate particle in the Standard Model. Dark energy, which drives the accelerating expansion of the universe, has no explanation in the model. Gravity itself, the most familiar force in everyday experience, has no place in the Standard Model. There is no quantum theory of gravity that successfully integrates with the rest of the framework. The Standard Model and Einstein's general relativity, which describes gravity as the curvature of space-time, are both extraordinarily successful in their respective domains, and yet they are fundamentally incompatible with each other at the mathematical level. This is one of the deepest tensions in all of physics. Two theories, each confirmed to extraordinary precision within its domain. And yet they cannot both be right in the same complete sense, because they rest on different foundations and make predictions that conflict at extreme scales. Mere black holes, at the moment of the Big Bang, in the very early universe when quantum effects and gravitational effects were both enormous simultaneously. Something lies beyond. A deeper theory, perhaps, one that reduces to general relativity in one limit and to quantum mechanics in another, the way those theories themselves reduce to classical Newtonian physics at the scales of everyday life. Physicists have various candidates: string theory, loop quantum gravity, and others. None has yet made a prediction that experiments have confirmed. None has achieved the kind of observational validation that would elevate it from a candidate to a theory. And so particle physics stands at a remarkable threshold. Armed with the most powerful instruments ever built, having confirmed a framework of extraordinary elegance and precision, and yet clearly seeing the edges of that framework, the places where it goes quiet, where the map runs out and the territory continues. Neutrino oscillation pointed to one of those edges. The absence of a dark matter particle in the LHC's data has pointed to others. The incompatibility of quantum mechanics and gravity traces the largest edge of all. The Standard Model is not wrong. But it is not finished. It is, in the language physicists sometimes use, an effective theory, one that works beautifully within a certain range of energies and scales, and that will eventually be understood as a limiting case of something more complete. The history of physics is, in many ways, the history of discovering those limits, of finding the places where the current best theory fails to capture everything, and using those failures as guides towards something deeper. Newton's mechanics was extraordinarily successful for over 2 centuries before it was revealed to be an approximation of something more general. The same will almost certainly be true of the Standard Model. What that something more general looks like, what the deeper theory is, what particles or structures or symmetries it reveals, no one yet knows. The experiments continue. The data accumulates. The theories are refined, tested, challenged, and occasionally overturned. In enormous underground detectors watching for neutrino oscillations, in the collision chambers of the LHC where proton beams cross at energies that briefly echo the first moments of creation, in observatories scanning the sky for signals from the early universe, in all of these places, the search continues. The particle zoo, as it was once called, that bewildering collection of subatomic particles cataloged through decades of experiment, turned out to have a hidden order. The Standard Model revealed that order, organized it, explained it. And in doing so, it also revealed that the order runs deeper still, that there are layers beneath the layers we have found, questions beneath the questions we have answered, a universe more intricate and more strange than any single theory has yet fully captured. That is not a cause for frustration. It is, if anything, a cause for a quiet kind of wonder. The universe has been telling us its secrets, one experiment at a time, for centuries. And it has not yet run out of things to say. There is a field that permeates all of space. Every cubic centimeter of the universe, from the interior of stars to the emptiness between galaxies, is filled with it. You cannot see it, cannot feel it, cannot detect it with any ordinary sense. And yet without it, atoms could not exist. Chemistry would be impossible. Stars could not form. The universe as we know it would simply not be there. This is the Higgs field. And understanding what it does requires stepping back for a moment to appreciate one of the stranger questions in physics. Why do particles have mass at all? Mass is so fundamental to our experience of the physical world that we rarely think to question it. Objects have mass. That is just how things are. But in the mathematics of quantum field theory, the framework underlying the Standard Model, particles are not little balls with mass attached. They are excitations of quantum fields, and the question of why those excitations resist acceleration, why they have inertia, why they behave as though they have weight, that is a question that requires an answer. It is not automatic. It has to come from somewhere. In the early 1960s, physicists working on the theory of fundamental forces noticed a deep problem. The mathematical symmetries that the Standard Model is built upon, the symmetries that make the theory work and that have since been confirmed with extraordinary precision, seemed, in their purest form, to require that certain particles be massless. The W and Z bosons, which carry the weak nuclear force, should have been massless according to the unbroken symmetry. But experiments showed they were not massless. They were, in fact, among the heaviest particles then known, nearly 100 times the mass of a proton. The symmetry was being broken somehow. and the theory needed to explain how. The answer came from several physicists working independently in 1964, among them Peter Higgs, Francois Englert, and Robert Brout. Their proposal was elegant in the way that the best physics ideas tend to be, not simple exactly, but fitting. They suggested that the vacuum of space is not truly empty or neutral. It is filled with a field, the Higgs field, that has a non-zero value even in its lowest energy state. And particles moving through this field interact with it, and that interaction is what gives them mass. The stronger a particle's interaction with the Higgs field, the more it is slowed and resisted, and the heavier it appears. The weaker the interaction, the lighter the particle. This is the Higgs mechanism. It is a way of breaking the mathematical symmetry of the Standard Model in a controlled, structured way, generating mass for certain particles while leaving others untouched. The W and Z bosons interact strongly with the Higgs field and are therefore heavy. The photon does not interact with the Higgs field at all and remains massless, which is why light travels at the speed it does, and why electromagnetism behaves so differently from the weak force despite their deep theoretical relationship. Quarks acquire mass through the Higgs mechanism. The charged leptons, the electron, the muon, and the tau acquire mass through it as well. Each has a different strength of coupling to the Higgs field, and that difference in coupling is reflected directly in their masses. The top quark, the heaviest of all known quarks, interacts with the Higgs field more strongly than any other known elementary particle, and its mass is enormous by subatomic standards, roughly as heavy as an entire gold atom, despite being a supposedly elementary, structureless particle. The electron, by contrast, couples to the Higgs field far more weakly, and its mass is correspondingly tiny. The hierarchy of particle masses, that strange ladder of values spanning many orders of magnitude, is, in the Higgs framework, a reflection of how strongly each particle couples to this all-pervading field. The Higgs mechanism was mathematically compelling from the beginning. But physics demands more than mathematical elegance. It demands experimental confirmation. And for nearly half a century, the Higgs boson, the particle associated with the Higgs field, the quantum ripple that a sufficiently energetic disturbance of that field would produce, remained undetected. It was the one piece of the Standard Model that had not been directly observed. Its mass could not be precisely predicted by the theory, only constrained within a range, and that range required collision energies that no accelerator before the LHC could reach. When the Large Hadron Collider at CERN began operating at full energy and the data from billions of proton collisions was analyzed, the signal emerged. On the 4th of July, 2012, the two large detector collaborations at the LHC, ATLAS and CMS, each involving thousands of physicists from institutions around the world, announced jointly that they had observed a new particle consistent with the long-predicted Higgs boson. The mass was approximately 125 times the mass of a proton. The properties matched what theory had predicted. The particle was real. It was a moment that those who witnessed it described as genuinely emotional. Not because of the spectacle, there was no explosion, no dramatic visual, just data on screens and a room full of physicists, but because of what it meant. A field predicted to fill all of space, a mechanism proposed to explain how matter acquires mass, a particle hypothesized nearly 50 years earlier, all of it confirmed in one announcement. Peter Higgs, who had proposed the field and its associated boson in 1964, was present in the auditorium at CERN that day. He was 82 years old. The Nobel Prize in Physics was awarded the following year, in 2013, to Peter Higgs and Francois Englert. But the discovery, for all its significance, immediately raised a question that remains unresolved. The Higgs mechanism gives mass to quarks, to charged leptons, to the W and Z bosons. These are the particles it was designed to explain. But what about neutrinos? Neutrinos have mass, we know that from oscillation experiments. But whether the Higgs mechanism is responsible for neutrino mass is genuinely unclear. The Standard Model, as originally written, did not include neutrino mass at all. The mechanism by which neutrinos acquire their tiny but non-zero mass is one of the open questions at the frontier of particle physics. One possibility, and a widely discussed one, involves what are called right-handed neutrinos, hypothetical particles that have not yet been observed, but whose existence would allow a mass generation mechanism different from the standard Higgs coupling. Another possibility, even more intriguing, involves the idea that neutrinos might be what are called Majorana particles, particles that are their own antiparticles. If true, this would be unique among known fundamental particles, and it would have profound implications for why the universe contains more matter than antimatter. Experiments are underway, searching for a hypothetical process called neutrinoless double beta decay, that would confirm or rule out the Majorana possibility. So far, no signal has been found. The search continues. The uncertainty about neutrino mass is a small but telling example of something larger, that the Standard Model, for all its achievements, is not a complete theory. It is not the final word. And as we look more carefully at its structure, the places where it is silent become increasingly conspicuous. The most obvious gap is one we have touched on already: gravity. The Standard Model describes 3 of the 4 known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It does not describe gravity. Gravity, in the Standard Model, simply has no place. There is no graviton, the hypothetical force-carrying particle of gravity, in the Standard Model's framework, and attempts to include gravity using the same quantum field theory approach that works for the other forces run into severe mathematical problems. The calculations produce infinities that cannot be removed in any controlled way, what physicists call non-renormalizability, and so the approach fails. Gravity is instead described by Einstein's general theory of relativity, a classical, non-quantum theory in which gravity is not a force carried by particles but a curvature of spacetime itself caused by mass and energy. General relativity is spectacularly successful at the scales where gravity matters most: planetary motion, the bending of light around massive objects, the behavior of black holes, the expansion of the universe. It has been tested with extraordinary precision and never found wanting within its domain. But it is not a quantum theory. And at the scales where quantum effects become relevant, near the singularities inside black holes, at the moment of the Big Bang, it breaks down. It cannot be the final answer either. Two theories. Both confirmed. Both incomplete. Both pointing towards something beyond themselves. The unification of quantum mechanics and general relativity into a single consistent framework is arguably the central unsolved problem of theoretical physics. It has been worked on by some of the greatest minds of the past century, and it remains unsolved. The mathematics is ferociously difficult. The energy scales at which quantum gravitational effects would be directly observable, the Planck scale, are so far beyond anything any accelerator could ever reach that direct experimental tests seem, for now, essentially impossible. Progress is being made through indirect reasoning, through mathematical consistency arguments, through the study of black holes and the early universe, where both theories must somehow apply simultaneously. But the solution remains out of reach. And then there is dark matter. This is perhaps the most striking gap of all, because it is not a gap in the theory's internal mathematics. It is a gap between the theory and the observed universe. The Standard Model accounts for all the particles that make up ordinary matter: protons, neutrons, electrons, the atoms and molecules and compounds from which everything visible is constructed. But ordinary matter, it turns out, is not most of what is out there. The evidence for dark matter has been accumulating since the 1930s. When the Swiss astronomer Fritz Zwicky noticed that galaxies in a cluster were moving too fast, far faster than the gravitational pull of the visible matter in the cluster could account for. If only the visible matter were present, the galaxies should fly apart. They do not. Something is holding them together. Something with mass, and therefore gravity, but producing no detectable light, no electromagnetic radiation of any kind. Something dark. Decades of subsequent observation have made the case overwhelming. The rotation curves of individual galaxies, the way stars orbit around their galactic centers, show that outer stars move far too fast if only the visible matter is contributing to gravity. The large-scale structure of the universe, the way galaxies are distributed across cosmic scales, matches theoretical models far better when dark matter is included. The cosmic microwave background, the faint remnant glow of light from the early universe, contains patterns whose precise character depends on the amount and distribution of dark matter, and those patterns, measured with exquisite precision by satellites like Planck, are consistent with dark matter constituting roughly 27% of the total energy content of the universe. Ordinary matter, everything described by the Standard Model, everything you can see and touch and build and measure, makes up only about 5%. Dark matter outweighs ordinary matter by approximately 5 to 1. We are, in a very real sense, living in the thin luminous fringe of a much larger invisible universe. And yet we have not detected a single dark matter particle directly. Experiments buried deep underground, designed to catch the faint recoil that would occur if a dark matter particle collided with an atomic nucleus, have been operating for years. They have found nothing definitive. Searches at the LHC for particles that might serve as dark matter candidates have come up empty. Indirect detection experiments, looking for signals from dark matter particles annihilating each other in the centers of galaxies, have produced suggestive hints but no confirmed detection. Whatever dark matter is made of, It interacts with ordinary matter so weakly that it has so far evaded every trap we have set. The leading candidate for decades was a class of particles called WIMPs, weakly interacting massive particles. They were theoretically attractive because they arose naturally in extensions of the Standard Model, particularly in a framework called supersymmetry, and because they would have been produced in the right abundance in the early universe to account for the observed dark matter density. But the non-detection of WIMPs in increasingly sensitive experiments has put pressure on the simplest versions of this idea. Some physicists are exploring other candidates: axions, sterile neutrinos, primordial black holes, and others. The question remains genuinely open. And if dark matter is the larger mystery in terms of mass, dark energy is the larger mystery in terms of effect on the universe's fate. In 1998, two independent teams of astronomers studying distant supernovae, using these stellar explosions as distance markers to map the expansion of the universe, made a discovery that surprised almost everyone, including the scientists themselves. The expansion of the universe is not slowing down, as gravity would suggest it should. It is accelerating. Galaxies are flying apart from each other at an increasing rate, driven by something that acts in opposition to gravity, something that fills space and pushes outward rather than pulling inward. This something is called dark energy. And it is, by current measurements, the dominant component of the universe, constituting roughly 68% of its total energy content. Dark matter makes up 27%. Ordinary matter makes up 5%. The universe we can see, touch, and describe with the Standard Model accounts for 1/20th of what is actually out there. Dark energy has no explanation in the Standard Model. The simplest interpretation is that it is a property of space itself, that empty space has an intrinsic energy density, sometimes called the cosmological constant. Einstein actually introduced this concept, somewhat reluctantly, into his equations of general relativity in 1917, then abandoned it when the universe appeared to be static, then watched it be vindicated 7 decades later when the accelerating expansion was discovered. The mathematics permits it. But explaining from first principles why the cosmological constant has the value it does, rather than being zero, or rather than being vastly larger than it is one of the most profound unsolved problems in theoretical physics. Attempts to calculate the value of the vacuum energy from quantum field theory produce a result that differs from the observed value by something in the range of 120 orders of magnitude. This is considered the worst quantitative prediction in the history of physics, not because the theory is obviously wrong, but because the discrepancy points to something deep and unresolved about how quantum mechanics and gravity interact at the level of the vacuum. So we find ourselves in an extraordinary position. Equipped with the most successful and precisely tested theory of matter and forces ever developed. Holding in our hands the confirmed discovery of the Higgs boson, the last predicted piece of a framework built over decades by thousands of physicists across generations. And simultaneously facing the fact that this framework, for all its power, describes only a small fraction of the universe. The gravity that shapes spacetime on the largest scales has no place in it. The dark matter that makes up the scaffolding of cosmic structure is invisible to it. The dark energy that determines the ultimate fate of the universe lies entirely beyond it. The Standard Model is not wrong. It is one of the great achievements of human thought. But it is, unmistakably, a beginning, not an end. A foundation that has been laid with extraordinary care and precision, on top of which something larger waits to be built. Physicists sometimes describe this moment in the history of their field as one of deep tension. The tools available, both experimental and theoretical, are more powerful than ever before. The data is more precise than ever before. And yet the next breakthrough, the insight that will open the door beyond the Standard Model, has not arrived. There is a sense of standing at the edge of a map, knowing the territory continues, but not yet able to see what lies beyond the boundary. That feeling, of knowing how much has been understood, and simultaneously how much remains unknown, is perhaps one of the most human experiences in science. It is not discouraging. It is, for those who spend their lives at this frontier, what makes the work worth doing. Every gap in the Standard Model is not a failure. It is an invitation. A signal that the universe still has secrets to offer, if we can find the right way to ask. The Higgs field fills all of space, giving mass to the particles that make up everything we can see. Beyond it, in the dark and silent majority of the cosmos, something else fills space too, something we have measured but not touched, named but not understood, mapped in outline but not in detail. The universe is mostly dark and mostly unknown. And that, quietly, is one of the most wonderful things about it. There is a number that sits at the heart of one of the deepest mysteries in all of science. It is not a large number. It is not dramatic in appearance. But what it represents, what it tells us about why anything exists at all, is perhaps the most profound question physics has ever confronted. For every billion antiparticles produced in the first moments after the Big Bang, there were 1,000,000,001 particles of ordinary matter. A difference of 1 part in a billion. That tiny excess, that almost imperceptible imbalance, is the reason the universe contains galaxies, stars, planets, and life rather than nothing but light. When matter and antimatter met and annihilated each other in the first fractions of a second, that 1 in a billion surplus of matter survived the catastrophe. Everything you have ever seen, everyone you have ever known, every atom and every object in the observable universe, all of it descended from that razor-thin margin. The Standard Model cannot explain it. This is not a minor gap. It is not a detail to be filled in later with a small correction. The matter-antimatter asymmetry of the universe is a fundamental feature of reality, written into the large-scale structure of everything that exists, and the most successful theory of particle physics we have offers no satisfactory account of how it arose. This is one of the most important clues, perhaps the most important clue, that the Standard Model is incomplete. That something lies beyond it, waiting to be discovered. Physicists use the term baryogenesis to describe the theoretical process by which this asymmetry was generated. Baryons are the class of particles that includes protons and neutrons, the particles that make up atomic nuclei, the building blocks of ordinary matter. Baryogenesis, therefore, is the origin story of all ordinary matter in the universe. How did the universe come to contain more baryons than antibaryons? What physical process, in the first instance after the Big Bang, tipped the scales in favor of matter? For any viable baryogenesis mechanism to work, three conditions must be met. These were identified in 1967 by the Soviet physicist Andrei Sakharov, and they are known as the Sakharov conditions. First, there must be processes that violate the conservation of baryon number, that is, processes that can change the total count of baryons in the universe. Second, there must be a violation of certain symmetries in nature, specifically CP symmetry, which relates to the behavior of particles versus antiparticles. And third, these processes must have occurred out of thermal equilibrium, meaning in conditions where the universe was expanding and cooling fast enough that reactions could not simply run backward and erase the asymmetry as quickly as it was created. The Standard Model satisfies the first and third conditions, at least in principle. But it fails on the second. The amount of CP violation built into the Standard Model, the degree to which particles and antiparticles behave differently, is far too small to account for the observed excess of matter. The asymmetry we see in the universe requires significantly more CP violation than the Standard Model contains. And that shortfall is one of the clearest experimental signals that new physics must exist, physics beyond the Standard Model, containing new sources of CP violation that have not yet been identified or detected. This is, in a sense, the universe handing us a clue. The very fact that we exist, that atoms exist, that stars burn and planets orbit, all of this is evidence that something happened in the early universe that the Standard Model cannot describe. Our existence is the anomaly. The ordinary world is the fingerprint of new physics. It is worth pausing to appreciate the remarkable way in which particle physics and cosmology have become intertwined in addressing these questions. These were once considered entirely separate disciplines. Cosmology concerned itself with the large galaxies, the expansion of the universe, the geometry of space-time. Particle physics concerned itself with the unimaginably small quarks, leptons, the forces between them. But as both fields matured, it became clear that they were studying different aspects of the same story. The universe in its earliest moments was a particle physics experiment of unimaginable scale and energy. The conditions that existed in the first trillionths of a second after the Big Bang, temperatures and energy densities so extreme that no particle accelerator has come close to replicating them, determine the composition of the universe for all time. The relic abundance of cold dark matter is another example of this convergence. Cold dark matter refers to dark matter particles that were moving slowly relative to the speed of light at the time they decoupled from the hot plasma of the early universe, a characteristic that affects how they cluster and form structures. The amount of cold dark matter we observe today, that 27% of the universe's total energy content, is a number that depends on the properties of dark matter particles in the early universe, their mass, how strongly they interacted with other particles, and at what point they stopped being produced in significant quantities as the universe expanded and cooled. For WIMPs, the weakly interacting massive particles that were long the leading dark matter candidate, the predicted relic abundance matched the observed dark matter density remarkably well. This coincidence, sometimes called the WIMP miracle, made WIMPs theoretically compelling for decades. a particle with roughly the mass of the W or Z boson, interacting through the weak force, produced in the conditions of the early universe, would naturally survive in the right amount to account for all the dark matter we observe today. The theory seemed almost too good to be correct. And then the experiments ran and found nothing. This is the uncomfortable situation particle physics now finds itself in. The theoretical arguments pointing toward new physics are strong, in some cases, overwhelming. The experimental evidence for what that new physics actually is remains elusive. The two things that particle physicists most confidently expected to find at the LHC, supersymmetric particles and dark matter candidates, have not appeared. The Higgs boson was found, and its discovery was a triumph. But the other new particles that many theorists expected to accompany it at the LHC's energy scale have not shown up in the data. This does not mean the theories are wrong. It may mean the new particles are heavier than current accelerator energies can produce. It may mean we are looking in the wrong place, or with the wrong instruments, or that the theoretical frameworks guiding our searches need revision. Science often progresses through exactly this kind of frustration, a period where the expected discoveries do not materialize, forcing a reassessment of assumptions and eventually leading, sometimes after decades of difficulty, to a genuinely new understanding. The search for physics beyond the Standard Model is now one of the most active and intensely competitive areas of research in all of science. It is driven not by one anomaly but by several, each pointing in the same general direction, toward the existence of a deeper, more complete theory of which the Standard Model is only a piece. One of the most promising conceptual frameworks proposed to extend the Standard Model is supersymmetry, often abbreviated as SUSY. Supersymmetry is a mathematical symmetry that relates the two fundamental classes of particles, fermions, which are matter particles like quarks and electrons, and bosons, which are force-carrying particles like photons and gluons. In a supersymmetric theory, every known particle has a partner particle, a superpartner, with the same charge and interactions but a different spin. The superpartner of the electron is called the selectron. The superpartner of the quark is the squark. The superpartner of the photon is the photino. None of these particles have been observed. Supersymmetry is attractive for several reasons beyond simply providing dark matter candidates. It naturally addresses a subtle but mathematically serious problem in the Standard Model called the hierarchy problem, the question of why the Higgs boson has the mass it does, rather than being either massless or enormously heavier due to quantum corrections. In a supersymmetric theory, these quantum corrections cancel between particles and their superpartners in a way that keeps the Higgs mass at its observed value without requiring delicate fine-tuning. The mathematics works out more naturally. The theory feels more stable. Supersymmetry also has the remarkable property that, if it exists, the coupling strengths of the three non-gravitational forces, electromagnetism, the weak force, and the strong force, converge to a single value at very high energies, in a way that does not quite happen in the Standard Model alone. This convergence suggests that at extremely high energy scales, the three forces may be unified into a single force described by a single underlying theory. This idea is called grand unification, and theories that achieve it are called grand unified theories, or guts. They predict new phenomena, including the very slow decay of protons, which has not yet been observed but is being searched for in large underground detectors filled with ultrapure water and watched by thousands of light sensors. Beyond supersymmetry, there are other frameworks physicists are exploring. Extra dimensions, the idea that space has more than 3 spatial dimensions, with the additional dimensions curled up at scales too small to detect directly, arise naturally in string theory and other approaches, and could explain why gravity is so much weaker than the other forces. If extra dimensions exist, the LHC might produce microscopic black holes, tiny, instantly evaporating concentrations of energy, as a signature. None have been observed. But the search continues, and future higher energy colliders are being planned that could probe energy scales the LHC cannot reach. There are also approaches that do not involve supersymmetry at all, frameworks like compositeness, which proposes that the quarks and leptons we currently treat as elementary are themselves made of smaller constituents, just as protons were once thought to be elementary before quarks were discovered. Or Technicolor, which proposes an alternative to the Higgs mechanism based on new strongly interacting particles. These ideas have faced experimental challenges of their own, but they reflect the breadth of theoretical exploration underway. What all these approaches share is an underlying conviction that the Standard Model, for all its success, is a low-energy approximation of something more fundamental. A limiting case, the way Newtonian mechanics is a limiting case of special relativity at low velocities, or the way geometric optics is a limiting case of the full wave theory of light at large scales. The Standard Model works extraordinarily well at the energies we can currently probe. But at higher energies, at the scales that characterize the very early universe, at the Planck scale where quantum gravity cannot be ignored, it must break down. It is not expected to remain valid all the way up. Something new must take over. The question is what? And that question is not merely academic. It connects directly to the largest questions about the nature and fate of the universe. What is dark matter? Why is there more matter than antimatter? Why does the universe have the particle content it does? 3 generations of matter particles, 4 forces, the specific spectrum of masses. Why is the Higgs mass what it is? Why is the cosmological constant so extraordinarily small compared to what quantum field theory predicts? These are not separate puzzles. They are facets of a single, deeper question about why the universe is the way it is rather than some other way. And they are all pointing, collectively, in the same direction, beyond. There is something philosophically interesting about this moment in physics. We have built, through roughly a century of experimental and theoretical work, a framework of remarkable power and elegance. We have confirmed it to extraordinary precision. We have found every particle it predicted, culminating with the Higgs boson in 2012. And yet the framework itself, its practitioners are confident, is not the final answer. It is a triumph that is simultaneously a waypoint. A map that is extraordinarily detailed and accurate within a certain region, and that has clear edges marking where the unmapped territory begins. Those edges are not failures. They are, in the history of science, typically where the most important discoveries have been waiting. the anomaly in the orbit of Mercury that Newtonian mechanics could not fully explain, that was the edge that pointed toward general relativity. The ultraviolet catastrophe, the failure of classical physics to correctly describe the radiation emitted by hot objects, that was the edge that led to quantum mechanics. The gaps in the Standard Model, dark matter, dark energy, matter-antimatter asymmetry, quantum gravity, these are the edges of our current best theory, and they are where the physics of the next century is most likely to emerge. The search being conducted now, in underground laboratories watching for dark matter recoils, in detectors looking for proton decay, in careful measurements of the properties of B mesons searching for new sources of CP violation, in the next generation of neutrino experiments, in gravitational wave observatories detecting the ripples of colliding black holes. All of this is the process of probing those edges, of running experiments at the boundary of the known, watching for the signal that does not fit, the number that does not match, the particle that should not be there. Because that is how physics has always moved forward. Not by confirming what is already known, but by finding precisely where the known gives way to the unknown, and following that thread. The Standard Model is not expected to remain complete at very high energies. That sentence, understated as it is, contains within it the seeds of everything physics might become in the decades and centuries ahead. It is an acknowledgement that the current best theory of reality is provisional, not wrong, but partial. A chapter, not the whole story. And somewhere in the gap between what the Standard Model describes and what the universe actually does, in that space between the known and the unknown, the next chapter is waiting. It has always been waiting, in every era of physics. In the anomaly that does not fit, in the measurement that is slightly off, in the particle that does not appear when theory says it should, or in the particle that appears when theory says nothing should be there. The universe has always been more interesting than our best current description of it. And there is every reason to believe that will remain true for a very long time to come. The particles are still moving. The fields are still vibrating. The experiments are still running, in the quiet dark beneath mountains and polar ice and the Swiss-French border. The data is still coming in. And the universe, patient and precise and endlessly complex, is still waiting to be understood. Physics has a habit of revealing that what seems like a solved problem is, on closer inspection, merely a well-described one. The Standard Model describes how particles behave and interact with extraordinary precision. But description and explanation are not the same thing. And when you look carefully at the Standard Model, not at what it predicts, but at what it takes for granted, a series of puzzles come into view. Patterns that exist without explanation. Numbers that appear in the theory without any deeper justification for why they have the values they do. Coincidences that feel too specific to be coincidences, yet remain unaccounted for. These are not failures of the Standard Model in the sense of wrong predictions. They are silences, places where the theory works but does not explain why it works. And for physicists, silence of that kind is often more interesting than noise. Let us begin with the largest silence of all, gravity. In ordinary particle physics, at the energies accessible to current accelerators, at the scales of atoms and nuclei and even the most energetic cosmic ray collisions, gravity is essentially irrelevant. It is so incomparably weaker than the other three fundamental forces that it can be ignored entirely without affecting any prediction to measurable precision. Two protons approaching each other in a collision are influenced by the strong force, the weak force, and electromagnetism. Gravity between them is so vanishingly small that it has no detectable effect on the outcome whatsoever. And so the Standard Model simply leaves it out. For its intended domain, this is perfectly adequate. But there is a scale at which this ceases to be adequate. It is called the Planck scale, and it represents the energy at which gravity becomes as strong as the other forces, the energy at which quantum mechanical effects and gravitational effects are simultaneously important and cannot be treated separately. This energy is enormously higher than anything any accelerator could reach, higher, in fact, by many orders of magnitude than even the most optimistic proposals for future particle colliders. At the Planck scale, the smooth, continuous spacetime of general relativity presumably breaks down. Quantum fluctuations of spacetime itself become significant. The very concepts of position and distance, as we normally use them, may cease to apply. What happens at the Planck scale is, in the deepest sense, unknown. General relativity predicts the existence of singularities, points of infinite density inside black holes and at the moment of the Big Bang, but these singularities are widely understood to be a sign that the theory is breaking down, not a literal feature of reality. A quantum theory of gravity would, it is hoped, resolve these singularities and describe what actually happens in these extreme conditions. But without that theory, we simply cannot say. The early universe, in its first moments, was a Planck scale environment. The conditions that gave rise to everything, to the matter-antimatter asymmetry, to the density fluctuations that seeded galaxy formation, to whatever process set the initial values of the fundamental constants, occurred at energies and densities where quantum gravity cannot be ignored. Understanding the origin of the universe requires a physics we do not yet have. And building that physics is, in many ways, the central challenge of fundamental science in the 21st century. Supersymmetry, which we have touched on before, is among the most developed responses to this challenge. But it is worth spending a little more time with the specific problems that supersymmetry was designed to address, because they reveal something about how physicists think about what a good theory should look like. The most urgent of these problems, from a technical standpoint, is the hierarchy problem. It concerns the mass of the Higgs boson, specifically, the question of why that mass is as small as it is. In quantum field theory, the masses of particles are not simply fixed values. They receive contributions from quantum fluctuations, from virtual particles popping in and out of existence and interacting with the particle in question. For most particles, these contributions are manageable. But the Higgs boson is special. It couples to all the massive particles in the Standard Model, and the quantum contributions to its mass from these interactions are, in the absence of any cancellation mechanism, naturally of order the highest energy scale in the theory. If that scale is the Planck scale, the natural value of the Higgs mass would be roughly 10 to the power of 17 times larger than its observed value. The observed Higgs mass is approximately 125 times the mass of a proton. The naturally expected value, without any fine-tuning, would be around 10 to the 18th times the proton mass. To get from the natural value to the observed value, the various contributions to the Higgs mass would have to cancel each other with a precision of roughly 1 part in 10 to the 32. That level of cancellation, maintained through all the complexity of quantum corrections, strikes most physicists as implausible, not impossible, but deeply unnatural. It feels like a coincidence of a kind that physical theories do not usually require. Supersymmetry resolves this problem elegantly. For every particle contributing a positive quantum correction to the Higgs mass, the corresponding superpartner contributes an equal and opposite negative correction. The cancellations are automatic, a consequence of the symmetry itself rather than a fine-tuned accident. If supersymmetry is exact, the Higgs mass is naturally stabilized. If supersymmetry is broken, as it must be, since we do not observe superpartners with the same mass as their standard model counterparts, the cancellations are imperfect. But if the breaking occurs at the right scale, the Higgs mass remains naturally small compared to the Planck scale. The hierarchy is explained. This is why the LHC was expected, by many theorists, to find supersymmetric particles. If supersymmetry is solving the hierarchy problem, the superpartners should be relatively close in mass to the Higgs boson, within reach of LHC energies. Their absence in the data so far has not killed the idea, but it has pushed the viable parameter space into regions that require more fine-tuning than the theory was originally meant to avoid. The tension is real, and it is taken seriously. There is another puzzle, less famous than the hierarchy problem but equally deep, called the flavor puzzle. It concerns the pattern of masses of the fundamental particles, and when you look at those masses carefully, what you find is deeply strange. The quarks span an enormous range of masses. The up quark, one of the constituents of the proton, has a mass of roughly 2 to 3 megaelectron-volts. The top quark, also an elementary particle, with no known internal structure, apparently just as fundamental as the up quark, has a mass of about 173 gigaelectron-volts. That is a difference of roughly 80,000 times between two particles that are, in every other respect, structurally identical. They have the same spin, the same type of interactions, the same role in the Standard Model's architecture. Their masses differ by almost 5 orders of magnitude. The same pattern appears in the charged leptons. The electron, the muon, and the tau are identical in all their quantum numbers except mass. The muon is about 200 times heavier than the electron. The tau is about 17 times heavier than the muon. Why? The Standard Model does not say. The masses enter the theory as free parameters, numbers that must be measured experimentally and inserted by hand, with no theoretical prediction or explanation for their values. The same is true of the quark masses, the mixing angles between quark generations, and a phase parameter related to CP violation. The Standard Model accommodates all of these numbers. It does not explain any of them. The flavor puzzle is the question of why these numbers have the values they do. Why are the 3 generations of matter particles arranged as they are, with the specific mass ratios they have? Is there a deeper symmetry or structure that determines these values, a theory of flavor that, once found, would explain the pattern the way the periodic table structure was eventually explained by quantum mechanics? Most physicists suspect the answer is yes. But no such theory has been confirmed. The flavor structure of the Standard Model remains one of its most conspicuous unexplained features. Then there is the strong CP problem. This one requires a little unpacking, but it is worth following the thread, because it leads somewhere genuinely strange. CP symmetry, as we discussed earlier, relates to the combined behavior of particles and antiparticles under certain transformations. Its violation is what allows matter and antimatter to behave differently, and its violation in the weak force is, in fact, observed experimentally and built into the Standard Model. But the strong force, the force that binds quarks into protons and neutrons, also permits CP violation, according to the mathematics of the theory. There is a parameter in the equations of quantum chromodynamics, the theory of the strong force, that, if non-zero, would cause the strong force to violate CP symmetry. Experiments measuring the electric dipole moment of the neutron, which would be non-zero if strong CP violation occurred, have found no signal. The parameter appears to be extraordinarily small, consistent with 0, or at most about 10 to the negative 10. Why? The mathematics permits values up to order 1. There is nothing in the theory that requires this parameter to be small. And yet it appears to be vanishingly small, perhaps exactly 0. This unexplained smallness is the strong CP problem. It is a fine-tuning puzzle of a different flavor from the hierarchy problem, but equally without a natural explanation in the Standard Model. One of the most elegant proposed solutions was introduced by physicists Roberto Pecchiai and Helen Quinn in 1977. They proposed a new symmetry of nature that, when spontaneously broken, would dynamically drive the strong CP parameter to 0 automatically, as a consequence of the physics, rather than by fine-tuning. This symmetry predicts the existence of a new particle, called the axion, first named by Frank Wilczek. The axion would be extremely light and extremely weakly interacting, making it almost as difficult to detect as a neutrino, but through different means. Remarkably, axions also turn out to be viable dark matter candidates. A universe filled with a sea of extremely light, extremely weakly interacting axions produced in the early universe could account for the observed dark matter density. Two deep problems, the strong CP problem and the nature of dark matter, might have a single solution. Searches for axions are underway using a variety of experimental techniques. Some experiments exploit the fact that axions, in the presence of a strong magnetic field, can convert into photons, producing a faint but potentially detectable signal. The ADMX experiment in the United States, and several others around the world, are searching this way. So far, no confirmed detection. But the searches are becoming more sensitive every year, probing deeper into the parameter space where axions might live. Now we come to something that, in a different kind of science, might be called a creation story. The story of the proton, and the question of whether it will last forever. Protons are, by any measure, extraordinarily stable. The current experimental lower limit on the proton's lifetime, the minimum time it would take for half of any given sample of protons to decay, is more than 10 to the 34th years. That number is so large it is almost meaningless to state in ordinary terms. The age of the universe is approximately 14 billion years, or about 10 to the 10th years. The proton's lifetime, if it decays at all, is at least 10 to the 24th times longer than the current age of the universe. For all practical purposes, the proton is eternal. And yet physicists suspect it may not be truly stable. Not because of any observational evidence for decay, none has ever been seen, but because of what theory suggests. In the Standard Model, proton stability is effectively guaranteed by a conservation law called baryon number conservation. The total number of baryons in any interaction is conserved, cannot increase or decrease. Since the proton is the lightest baryon, it has nothing to decay into without violating this law. And so it persists. But baryon number conservation is not a deep symmetry of nature in the way that energy conservation or charge conservation are. It is, in the language of physicists, an accidental symmetry, one that happens to hold within the Standard Model but is not required by any deeper principle. And in virtually every proposed extension of the Standard Model, in grand unified theories, in supersymmetric theories, in string-inspired models, baryon number conservation is violated. Processes that convert quarks into leptons, changing the baryon number of the universe, are possible in these theories. And if such processes are possible, then protons can, in principle, decay. The predicted rate of proton decay depends enormously on the details of the theory. In the simplest grand unified theories, protons would decay with a lifetime of roughly 10 to the 31st years, which the best experiments have already ruled out. In more sophisticated theories, the predicted lifetime is longer, 10 to the 34th or 35th years, or even longer still, within or just beyond the current experimental reach. The search for proton decay is one of the most patient experiments in all of science. It requires enormous detectors filled with ultrapure water or other materials, watched by thousands of light sensors, buried deep underground to shield them from cosmic ray backgrounds. The Super Kamiokande detector in Japan, that 50,000-ton tank of ultrapure water we mentioned earlier in the context of neutrinos, is also one of the world's leading proton decay searches. A successor experiment, Hyper Kamiokande, with roughly 10 times the volume, is under construction. Similar efforts are underway with other detector technologies in other countries. If proton decay is ever observed, it would be one of the most significant discoveries in the history of physics. It would immediately rule out the Standard Model as a complete description of nature at all energies, confirm that grand unification is real, and provide direct evidence for physics at energy scales far beyond anything a particle accelerator could ever reach. The proton's decay would be a message from the Planck scale physics of the early universe, encoded in the slow disintegration of ordinary matter. And consider what that means for the long future of the universe. If protons are truly stable, if baryon number is genuinely conserved even beyond the Standard Model, then the matter of the universe persists indefinitely, long after the stars have burned out and the black holes have evaporated, in a cold and dark and nearly featureless cosmos. But if protons decay, then eventually, over timescales that dwarf the current age of the universe by many orders of magnitude, all ordinary matter dissolves. Every atom, every molecule, every remnant of the physical world as we know it, gradually converts into lighter particles and radiation. The universe ends not with a bang, and not exactly with silence, but with an imperceptibly slow dissolution of matter itself. The answer to whether protons decay is thus not merely a technical question about particle physics. It is, in the deepest sense, a question about the ultimate fate of the material world. In inflation, the rapid exponential expansion of the universe believed to have occurred in the first tiny fraction of a second after the Big Bang, adds yet another layer to this picture. Inflation was proposed in the early 1980s, primarily by physicist Alan Guth, as a solution to several puzzles in standard Big Bang cosmology: why the universe is so uniform in temperature across regions that should never have been in causal contact, why its spatial geometry is so close to perfectly flat, and why no magnetic monopoles, particles predicted by grand unified theories, are observed today. Inflation solves all of these problems at once, by positing that the early universe underwent an extraordinary burst of expansion, doubling in size perhaps 60 or more times over an interval far shorter than a trillionth of a second, smoothing out any initial irregularities and diluting any unwanted relics to negligible densities. Inflation also provides the seeds of all cosmic structure. Quantum fluctuations in the field driving inflation, tiny, random variations at the quantum scale, were stretched to macroscopic and eventually cosmic scales by the expansion. Those fluctuations became the slight variations in density that, over hundreds of millions of years, gravitationally collapsed into galaxies, clusters of galaxies, and the large-scale web of filaments and voids that characterizes the observable universe today. The pattern of those primordial fluctuations is imprinted in the cosmic microwave background, the faint afterglow of the Big Bang, and has been measured with exquisite precision. The measurements match the predictions of inflation remarkably well. And yet inflation, like dark matter in baryogenesis, has no home in the Standard Model. The inflaton, the field responsible for inflation, is not any of the known particles. It is something additional, something beyond the current framework, something that must be added to the theory by hand. Its connection to the other fields and particles of the Standard Model is unknown. Whether inflation can be embedded in a deeper unified theory, and what the properties of the inflaton field tell us about physics at the highest energies, are active areas of theoretical research. What emerges from all of this, from the hierarchy problem, the flavor puzzle, the strong CP problem, the question of proton stability, the need for new physics to drive inflation, is a portrait of the Standard Model as a structure of extraordinary achievement surrounded on all sides by open questions. Each of the puzzles we have described represents a direction in which new physics is expected to lie. Each is a specific, well-defined challenge that any deeper theory must address. Together, they form a kind of map of the unknown, not a blank void, but a detailed outline of the territory that physics has not yet charted. The search is not random. It is guided by anomalies, by theoretical inconsistencies, by the specific patterns and gaps that the Standard Model itself reveals when examined carefully enough. The next physics, whatever it turns out to be, must account for dark matter and dark energy. It must explain baryogenesis. It must address the hierarchy problem and the flavor puzzle. It must either explain why protons are stable or predict a decay rate that experiments can search for. It must, ultimately, include a quantum theory of gravity. These are not modest requirements. They define a physics that would be deeper and more unified than anything we currently have, a theory that the Standard Model would emerge from as a limiting case, the way simpler theories emerge from more complete ones throughout the history of science. The Planck scale sits at the edge of what we can currently reach or even probe indirectly. Between the energies accessible to the LHC and the Planck scale lie many orders of magnitude of unexplored territory. What lives in that territory, what fields, what particles, what symmetries, what structures, is genuinely unknown. It is one of the great open frontiers in human knowledge. And it is being approached from multiple directions simultaneously, from the very small, through particle accelerators and precision measurements, from the very large, through cosmological observations of the early universe and the large-scale structure of space-time, and from the very precise, through experiments that measure tiny deviations from Standard Model predictions in well-controlled laboratory settings. The frontier is wide, and the physicists working along it are, in their patient and methodical way, closing in. Somewhere in all of this, in one of these searches, in one of these experiments, in one of these theoretical frameworks being tested against data, the next great discovery in fundamental physics is waiting. It may come as a new particle detected in an accelerator. It may come as a deviation in a precision measurement too small to explain within the Standard Model. It may come as a confirmed detection of proton decay, or of dark matter, or of a gravitational wave signature from the inflationary era. It may come from somewhere entirely unexpected, the way the greatest discoveries so often do. The universe is not finished revealing itself. It has been telling us its secrets for as long as we have had the instruments and the mathematics to listen. And every answer it has given has led, in time, to deeper questions, richer questions, stranger questions, questions that would not have been imaginable without the understanding that came before. That is the nature of this work. And in the quiet persistence of it, in laboratories and detectors and theoretical offices around the world, there is something genuinely beautiful. Not all discoveries begin with a dramatic signal. Not all of them arrive as a clear, unambiguous detection, a new particle lighting up a detector, a number that falls precisely where theory predicted. Some of the most significant clues in the history of physics have arrived quietly, as small disagreements. A measurement that comes out slightly differently than expected. A number that is almost right, but not quite. A pattern that holds in every case but one. These small disagreements are, in many ways, more interesting than confirmations. A confirmation tells you that the theory works. A small disagreement tells you that something may lie just beyond it. Particle physicists have, over the past 2 decades, developed an increasingly refined set of tools for finding exactly these kinds of disagreements. The approach is elegant in its logic. Take a prediction of the Standard Model that can be calculated with high precision, measure the corresponding quantity and experiment with equally high precision, and compare the two. If they match, the Standard Model is vindicated once again. If they do not, if there is a statistically significant discrepancy between the theoretical prediction and the experimental result, then something is either wrong with the calculation, wrong with the measurement, or pointing toward new physics that the standard model does not contain. This is painstaking work. It requires controlling every possible source of error, understanding every background process that could mimic the signal of interest, and accumulating enough data that statistical fluctuations cannot be blamed for any apparent disagreement. Particle physics holds itself to a high standard. A result is not considered a discovery until it reaches what is called 5 sigma significance, meaning the probability of the observed result occurring by chance, if the standard model were correct, is less than about 1 in 3.5 million. Below that threshold, a discrepancy is a hint, an anomaly, something worth watching. Above it, it becomes a discovery. Right now, physics has several hints. None has yet crossed the 5 sigma threshold and become confirmed new physics. But they are being watched with close attention, measured with improving precision, and taken seriously by a significant portion of the particle physics community. Among the most carefully studied of these hints involve particles called bosons. A meson is a type of subatomic particle made of one quark and one antiquark, not a proton or neutron, but a different combination held together by the strong force. Bosons contain a bottom quark, one of the heavier quarks, belonging to the third generation, paired with a lighter antiquark. They are unstable and decay quickly into other particles, and it is in the details of those decays that interesting things can sometimes be found. The standard model makes precise predictions about how bosons should decay, which decay products should appear, and in what proportions. These predictions are the result of decades of theoretical work, incorporating the full machinery of quantum field theory, and they are generally trusted to be accurate at the % level or better. Experiments at facilities dedicated to studying boson decays, most prominently the LHCb detector at the Large Hadron Collider, which is specifically designed for this kind of precision flavor physics, have measured these decay rates and compared them to theory. And for years, certain measurements have not quite agreed. Specific decay modes involving the tau lepton, the heaviest of the 3 charged leptons, have appeared to occur slightly more often than the standard model predicts, relative to decays involving the lighter leptons. This pattern, if real, would suggest that the 3 generations of leptons are not treated with exact equality by the forces involved, a violation of what physicists call lepton universality. The standard model assumes that the electromagnetic and weak forces couple identically to all 3 lepton generations, differing only because the leptons themselves have different masses. A genuine violation of lepton universality would be new physics. The hints have been suggestive, reaching statistical significances of around 3 sigma at various points, intriguing, but not definitive. Some have been updated as more data came in and theoretical calculations were refined. Some have persisted. The experimental and theoretical communities are working carefully to determine whether these anomalies are robust, whether they represent real deviations from the standard model, or whether they will dissolve into agreement as precision improves. That process is ongoing, and the answer is not yet settled. But there is another anomaly, longer standing, more precisely characterized, and in some ways more striking, that has drawn even wider attention. It involves the muon. The muon is, in most respects, simply a heavier electron. It carries the same electric charge, has the same spin, interacts through the same forces, and plays the same role in the second generation of leptons that the electron plays in the first. Its mass is about 207 times that of the electron, still far lighter than a proton, but heavy enough that it decays in about 2/millionths of a second into an electron and 2 neutrinos. In cosmic ray showers, muons are produced in enormous numbers when high-energy protons from space collide with the upper atmosphere, and they rain down on the Earth's surface continuously. At any given moment, roughly 1 muon is passing through each square centimeter of the Earth's surface every minute. What makes the muon so valuable as a probe of new physics is a property called its anomalous magnetic moment. This requires a little explanation, but it is worth following. Any charged particle with spin behaves like a tiny magnet. It generates a magnetic field, and it precesses in an external magnetic field the way a gyroscope precesses under gravity. The strength of this magnetic effect is characterized by a number called the G-factor. For a simple, structureless charged particle, the Dirac equation of quantum mechanics predicts that G should equal exactly 2. But in quantum field theory, virtual particles, those fleeting fluctuations of the vacuum we mentioned earlier, continuously interact with the muon, and these interactions shift the G-factor slightly away from 2. The deviation from 2 is called the anomalous magnetic moment, denoted G-2, or sometimes just AMU for the muon. This anomalous magnetic moment can be calculated from theory with extraordinary precision. The calculation involves summing contributions from virtual photons, virtual quarks, virtual W and Z bosons, and thousands of individual Feynman diagrams representing different quantum processes. The calculation is one of the most complex ever carried out in theoretical physics, and the result is known to better than 1 part per million. Crucially, if there are any undiscovered particles not in the standard model, they too would contribute to the muon's anomalous magnetic moment through virtual processes. Their contribution would be tiny, but potentially detectable if the measurement is precise enough. The measurement of the muon's anomalous magnetic moment has a long history. An experiment at Brookhaven National Laboratory in the United States, completed in the early 2000s, measured the quantity by injecting muons into a large circular magnetic storage ring and watching how their spin precesses as they circulate. The precision achieved was remarkable, and the result came out slightly higher than the standard model prediction. The discrepancy was about 3 to 4 sigma, suggestive, but not conclusive. The physics community watched this result for over a decade, waiting for the next generation of measurements. That next generation arrived with the muon G2 experiment at Fermilab in Illinois, an experiment that reused the actual storage ring magnet from the Brookhaven experiment, which was transported by truck and barge from New York to Illinois in a delicate operation that itself became something of a story. The Fermilab experiment accumulated far more data, with improved systematic controls, aiming to push the precision well beyond what Brookhaven achieved. When the first Fermilab results were announced in April 2021, they confirmed the Brookhaven discrepancy. The combined result reached a statistical significance of about 4.2 sigma, tantalizingly close to the 5 sigma threshold for discovery, but not quite there. The measured value of the muon's anomalous magnetic moment was consistently higher than the standard model prediction. Not by much, the difference was in the 8th or 9th decimal place of the g-factor, but by an amount that, if genuine, could not be explained by any known particle or process within the standard model. The implication, if the discrepancy is real, is that something is interacting with the muon that the standard model does not account for. Virtual particles from some undiscovered sector of physics, contributing to the muon's magnetic moment in the same way that known particles do, but through processes that currently have no theoretical description. The energy scale at which these hypothetical new particles might exist, estimated from the size of the discrepancy, points toward what physicists call the TeV scale, the range of energies from roughly 1 to 10 tera-electron volts. This is precisely the range that the LHC probes most directly, which makes the absence of direct detection of new particles in LHC data both relevant and puzzling. Either the new particles are there but have not yet been identified in the data, or the situation is more complicated than a simple new particle interpretation suggests. There is, however, an important caveat that has developed in parallel with the Fermilab measurements. The standard model prediction for the muon's anomalous magnetic moment is an extraordinarily complex calculation, and one portion of it, contributions from the strong force, involving the behavior of quarks and gluons at low energies, is particularly difficult to compute from first principles. This part of the calculation has traditionally relied on experimental data from electron-positron collisions to anchor the theoretical estimates. In 2021, a lattice QCD calculation, a powerful computational technique that evaluates quantum chromodynamics numerically on a discrete spacetime grid, produced a result for this strongly interacting contribution that differed from the data-based estimate in a direction that would reduce the discrepancy between theory and experiment. If the lattice result is correct, the theory prediction shifts upward, and the gap between theory and measurement narrows or potentially disappears. The situation now involves a genuine tension not just between theory and experiment, but between different theoretical approaches, and resolving it requires both improved lattice calculations and a better understanding of which experimental data provides the most reliable theoretical input. This is exactly the kind of careful, painstaking process through which physics actually advances. It is not always dramatic. It involves cross-checking calculations, identifying sources of systematic uncertainty, debating the reliability of different computational methods, and accumulating more data. The muon G2 experiment at Fermilab continues to collect data, and the final result, with the full dataset, will be substantially more precise. Lattice QCD calculations are improving every year as computing power increases and methods are refined. In the next few years, the situation should become clearer. If the discrepancy survives scrutiny, if both the experimental measurement and the theory prediction are confirmed at the precision required, then the muon's anomalous magnetic moment will become the most precisely established deviation from the standard model ever observed. It will not tell us exactly what the new physics is, but it will tell us, with high confidence, that something exists beyond the standard model and that it interacts with muons. That would be an extraordinary result, not a complete picture, but an unmistakable signal that the map of physics needs to be extended. And there is something fitting about the muon playing this role. It is, in many ways, one of the most overlooked particles in physics. When it was first discovered in cosmic rays in 1936, the physicist Isidore Rabi reportedly responded with the question, "Who ordered that?" The muon had not been predicted. It fit nowhere obvious in the theoretical frameworks of the time. It was simply there, a heavier, unstable copy of the electron, serving no apparent purpose in the structure of ordinary matter. Today, that same quality of being unexpected, of fitting uncomfortably, of being slightly off from what simple theory would suggest, makes it one of the most powerful probes of physics beyond the standard model. The very strangeness of the muon's existence, and the precision with which its properties can be measured, turns it into a kind of laboratory for new physics. An unexpected particle, pointing toward unexpected physics, in a discipline built on the willingness to follow the data wherever it leads. What all of these anomalies share, the B. Meson results, the hints of lepton universality violation, the muon's magnetic moment, is a character of smallness. They are not gaping holes in the theory. They are subtle cracks, narrow discrepancies, effects that require extraordinary precision to see and even more precision to confirm. The standard model is robust. It does not break down easily or obviously. It yields its secrets grudgingly, in fractions of a percent, in the 8th decimal place, in statistical significances that hover for years just below the threshold of certainty. This is what the frontier of fundamental physics looks like today. Not the dramatic discoveries of earlier eras, not the sudden appearance of the electron, or the detection of the first neutrino, or the observation of the W and Z bosons. Those days, for now, belong to history. The new physics, if it is there, is hiding behind extraordinary precision, and finding it requires measurements of a delicacy that would have seemed impossible a generation ago, driven by theoretical calculations of a complexity that required decades of collective effort to develop. But hiding is not the same as absent. The anomalies are real measurements, made by careful experimenters with well-understood instruments. Whether they survive as evidence of new physics, or resolve into agreement with the standard model as precision improves, the process of testing them is itself advancing our understanding. Every improved measurement, every refined calculation, every anomaly chased to its resolution, whether that resolution confirms new physics or vindicates the standard model, adds to the knowledge that guides the next search. Science proceeds this way, one careful measurement at a time. The universe does not hand over its answers freely. But it does leave clues, small ones, subtle ones, the kind that require patience and precision and an unflinching willingness to trust the numbers even when they are inconvenient. And somewhere in those numbers, in the tiny deviations and the almost agreements and the measurements that are almost right but not quite, somewhere in all of that, the next chapter of physics is quietly waiting to be read. There is a certain kind of experiment in physics that operates at the very edge of what is technically possible, where the measurement being attempted is so difficult, so demanding of precision, that building the apparatus at all is itself an achievement. These experiments are not looking for something large and obvious. They are searching for effects so small, signals so faint, that detecting them at all requires instruments of extraordinary sensitivity and years, sometimes decades, of careful operation. And yet the potential reward is immense. Because some of the most powerful constraints on new physics, some of the clearest windows into what lies beyond the standard model, come not from high-energy collisions that produce new particles directly, but from low-energy precision measurements that test the theory at a level of detail it was never designed to survive unchallenged. The neutron electric dipole moment is one of the most important of these searches. And understanding why requires a brief return to the concept of symmetry. CP symmetry, as we have discussed, relates to the behavior of particles and antiparticles, specifically, whether the laws of physics look the same when you simultaneously replace every particle with its antiparticle and reflect the spatial coordinates of the system. The standard model violates CP symmetry in the weak force, through a mechanism encoded in what is called the CKM matrix, a mathematical structure describing how quarks of different generations mix when they undergo weak interactions. This CP violation is real, experimentally confirmed, and beautifully incorporated into the theory. But the strong force presents a separate CP problem, which we touched on earlier. The mathematics of quantum chromodynamics, the theory of the strong force, contains a parameter, usually written as theta bar, that would, if non-zero, cause the strong force to violate CP symmetry. And strong CP violation would have a very specific, measurable consequence. It would give the neutron an electric dipole moment. An electric dipole moment means that the positive and negative charge distributions inside the neutron are not perfectly symmetric, that there is a slight separation between the centers of positive and negative charge, giving the neutron a tiny electric polarity, like a very faint bar magnet for charge rather than for magnetism. The standard model, with its observed value of theta bar close to zero, predicts that the neutron electric dipole moment should be extraordinarily small, far below current experimental sensitivity. But many extensions of the standard model, supersymmetric theories, various models of baryogenesis, predict a neutron electric dipole moment significantly larger than the standard model value, potentially within reach of current or near-future experiments. Measuring the neutron electric dipole moment, or placing tight limits on its size, is therefore one of the most powerful ways to test these theories without needing a particle accelerator at all. The measurement works by trapping ultracold neutrons, slowed to speeds of a few meters per second, cold enough to be stored in material bottles, and placing them in precisely controlled electric and magnetic fields. The spin of the neutron precesses in these fields at a rate that depends on both its magnetic dipole moment and, if it exists, its electric dipole moment. By comparing precession rates in parallel and antiparallel electric fields, any asymmetry caused by an electric dipole moment can be detected. The effect being searched for is extraordinarily small, equivalent to detecting a displacement of the neutron's charge center by a distance roughly 10 billion times smaller than the neutron itself. Experiments achieving this level of sensitivity are among the most technically demanding in all of physics. So far, no neutron electric dipole moment has been detected. Each generation of experiments has placed a tighter limit on its size, and each tighter limit has ruled out additional models of new physics and placed stronger constraints on the strong CP parameter theta bar. The current limit is at the level of about 10 to the negative 26 elementary charge times centimeters, an almost incomprehensibly small number, and yet future experiments aim to improve this by another order of magnitude or more. Every improvement either finds the signal, which would be revolutionary, or pushes the Standard Model's open problem even deeper and constrains new physics further. This is the logic of precision frontier experiments. You do not need to produce new particles to learn about them. Their virtual contributions to measurable quantities, their effects on the properties of known particles, their footprints and precision observables, all of these provide indirect but powerful evidence. The absence of a signal is itself information, ruling out theoretical possibilities and guiding the direction of the search. The same logic applies to a broader class of processes called rare and forbidden decays. The Standard Model predicts that certain particle decays should occur very rarely, suppressed by multiple factors in the quantum field theory calculation, while others are so strongly suppressed that they are effectively forbidden. Searching for these processes, and measuring their rates with precision, provides extremely sensitive tests of the theory. Any deviation from the predicted rate, a decay occurring more often than expected, or a process occurring that should essentially never happen, is a signal that something beyond the Standard Model is contributing. Among the most powerful of these searches involves a process called charged lepton flavor violation. In the Standard Model, the three generations of charged leptons, the electron, the muon, and the tau, are separately conserved in most interactions. A muon can decay into an electron and two neutrinos, but it does so in a way that conserves muon lepton number and electron lepton number separately, by producing one muon neutrino and one electron antineutrino. What it cannot do, in the Standard Model, is decay into an electron and a photon, a process that would change lepton flavor without any neutrinos to carry away the flavor quantum numbers. Such a decay is not absolutely forbidden by any fundamental principle. It is simply extraordinarily suppressed to a level so small that even with trillions of muon decays, not a single such event would be expected. The suppression arises because, in the Standard Model, the only way charged lepton flavor violation can occur at the quantum level is through loops involving neutrinos, and because neutrino masses are so tiny, the contribution from these loops is negligible. The predicted rate for muon to electron plus photon decay is so small, roughly 10 to the negative 54, that it is, for all practical purposes, zero. No experiment could ever observe it at that level. But here is the critical point. In many extensions of the Standard Model, supersymmetric theories, theories with extra dimensions, various models of new heavy particles, additional contributions to charged lepton flavor violation arise that are enormously larger than the Standard Model prediction, while still potentially being below current experimental limits. These theories predict rates that might be as large as 10 to the negative 13 or 14, still rare by everyday standards, but potentially observable with sufficient numbers of decays and a sensitive enough detector. Experiments searching for muon to electron plus photon, and for related processes like muon to 3 electrons, or muon to electron conversion in the presence of a nucleus, are among the most sensitive probes of new physics available. The MEG experiment at the Paul Scherrer Institute in Switzerland, which has been running and upgrading over more than a decade, has placed the world's best limit on the muon to electron plus photon decay rate. Its successor, MEG-2, is pushing sensitivity further. The Mu-2e experiment at Fermilab and the COMET experiment in Japan are searching for muon to electron conversion in nuclei with sensitivities that will improve on current limits by 4 orders of magnitude, meaning they will be 10,000 times more sensitive to new physics contributions than any previous experiment. Any observation of charged lepton flavor violation in these channels would be, without question, one of the most significant discoveries in the history of particle physics. It would be unambiguous, unequivocal evidence for physics beyond the standard model, a process that simply cannot occur at any observable rate within the current theory. It would immediately rule out large classes of models, confirm the existence of new particles or interactions, and provide crucial guidance for what those new particles might be. The field awaits these results with genuine anticipation. Then there is neutrinoless double beta decay. This is, in some ways, the most consequential search in all of low-energy particle physics, and the one whose implications, if a positive result were found, would reach furthest into our understanding of the fundamental nature of matter. Normal beta decay is a well-understood process in which a neutron inside an atomic nucleus converts into a proton, emitting an electron and an electron antineutrino. Double beta decay is a rarer process, occurring in certain nuclei where ordinary beta decay is energetically forbidden, in which 2 neutrons simultaneously undergo beta decay, producing 2 electrons and 2 electron antineutrinos. This process has been observed in a handful of isotopes and proceeds at a rate consistent with standard model predictions. Neutrinoless double beta decay is different. In this hypothetical process, the 2 electrons are emitted, but no antineutrinos accompany them. The antineutrino that would have been emitted by one neutron is absorbed by the other, participating in the second decay rather than escaping the nucleus. This can only happen if the antineutrino and the neutrino are the same particle, if the neutrino is what is called a Majorana fermion, a particle that is its own antiparticle. The implications of this are profound. If neutrinos are Majorana particles, it means that lepton number, the quantum number that counts the total number of leptons in a system, is not conserved. And lepton number violation is one of the necessary ingredients for certain mechanisms of baryogenesis, the process by which the matter-antimatter asymmetry of the universe was generated. There is a specific scenario, called leptogenesis, in which the decay of heavy Majorana neutrinos in the early universe produced an asymmetry in lepton number, which was subsequently converted into the baryon asymmetry we observe today, the excess of matter over antimatter that allows us to exist. Neutrinoless double beta decay would provide direct experimental confirmation that the neutrino is indeed a Majorana particle, lending crucial support to leptogenesis as the origin of matter. The experimental challenge is formidable. The process, if it occurs, is extraordinarily rare. The predicted half-life is at least 10 to the 26th years or longer, depending on the neutrino mass scale. To detect even a handful of events per year requires enormous detector masses, hundreds of kilograms to tons of the relevant isotope, along with extraordinary background suppression. These detectors must be shielded from cosmic rays, from environmental radioactivity, from the natural radioactivity of the detector materials themselves. They are built deep underground, assembled from materials selected for exceptional radio purity, and operated with extreme care. Several major experiments are pursuing this goal. The Goethe experiment in Italy's Gran Sasso laboratory used germanium-76 detectors and achieved world-leading background suppression. Its successor, Legend, is scaling up to hundreds of kilograms of germanium and eventually a ton, aiming for sensitivity that would probe Majorana neutrino masses down to the level implied by the measured neutrino oscillation parameters. The Kamlanzen experiment in Japan uses xenon-136 dissolved in liquid scintillator and has already placed the world's best limit on the half-life of neutrinoless double beta decay in xenon. NEXO, a proposed ton-scale liquid xenon detector, aims to push sensitivity further still. No experiment has yet observed neutrinoless double beta decay. The limits on its rate are extraordinarily stringent. But the searches are becoming more sensitive every few years, and the theoretical motivation for expecting a positive result, if neutrino masses arise through the seesaw mechanism, as many theorists believe, is strong. The next generation of experiments will either find the signal or rule out the simplest Majorana neutrino mass scenarios and force a rethinking of the theoretical framework. Each of these searches, the neutron electric dipole moment, the rare lepton processes, neutrinoless double beta decay, shares a common character. They are not looking for the spectacular. They are looking for the barely there. For effects so small that detecting them requires the most sensitive instruments human ingenuity has produced. For signals so rare that years of patient data collection are needed to accumulate even a handful of candidate events. This is precision physics at its most demanding, and, in many ways, at its most rewarding, because the questions it is asking are among the deepest in science. And now, from these deep underground searches, we turn to something that represents a different kind of frontier entirely. Not the frontier of the very small, exactly, but of the very delicate, a place where quantum mechanics and gravity, those two great incompatible frameworks of modern physics, are being brought into contact in the most careful, controlled way that current technology allows. Gravity is the most familiar force in human experience. We feel it constantly. We understand its effects at the scale of planets and people and falling objects with perfect clarity. And yet at the microscopic scale, at the scale of atoms and quantum particles, gravity has never, until very recently, been directly measured. It is simply too weak. The gravitational attraction between two electrons is roughly 42 orders of magnitude weaker than their electromagnetic repulsion. Measuring gravitational effects at the scale of individual particles or small collections of atoms requires an extraordinary leap in experimental capability. In 2022, an experiment achieved something that would have seemed essentially impossible a decade earlier. Physicists at the University of Vienna, working with colleagues at other institutions, successfully measured the gravitational force between two small masses, each weighing only about 100 milligrams, roughly the mass of a small insect, using a system sensitive enough to detect a force of about 30 femtonewtons. A femtonewton is a quadrillionth of a newton, one of the smallest forces ever directly measured in a laboratory setting. and the system used to make the measurement incorporated quantum mechanical elements, specifically, quantum superposition states of the mechanical oscillator used to sense the force, bringing the measurement into a regime where both quantum mechanics and gravity are simultaneously relevant. This is not yet quantum gravity in the full theoretical sense. It is not a probe of the Planck scale, not a test of any specific quantum gravity theory. But it is something genuinely new, a direct measurement of gravity at a scale where quantum effects matter, in a system where the two frameworks must be considered together. It demonstrates that experiments of this kind are possible, that the technical barriers to studying the intersection of quantum mechanics and gravity in the laboratory are not insurmountable. The implications for future experiments are significant. If gravitational forces can be measured at this level of precision using quantum mechanical systems, it opens the door to a new class of experiments that could test specific predictions of different quantum gravity approaches. Could superposition states of massive objects be used to test whether gravity causes wave function collapse, as some theories predict? Could precision gravitational measurements at the quantum scale reveal deviations from the inverse square law at short distances, as extra-dimension theories suggest? Could the gravitational interaction between two quantum systems create entanglement in a way that would be impossible if gravity were purely classical? These are not idle theoretical questions. They are now, in principle, experimentally accessible, not immediately, not with current technology, but within a foreseeable horizon of experimental development. The 2022 result was a proof of principle. A demonstration that the intersection of quantum mechanics and gravity is not purely a theoretical battleground, but a space that experiment can begin to explore. It is, in its quiet way, one of the most significant experimental results of recent years. Not because it answered a major question, but because it showed that a class of major questions can now be approached experimentally. The boundary between what can be tested and what must remain purely theoretical shifted, incrementally, carefully, but unmistakably. This is how science moves at its frontier. Not always in dramatic leaps, but in careful steps, each one extending the range of what is possible, each one opening new territory that was previously inaccessible. The neutron electric dipole moment experiments extend sensitivity by an order of magnitude. The lepton flavor violation searches improve their reach by 4 orders of magnitude. The double beta decay experiments probe half-lives that are a billion times longer than the age of the universe. And now, gravity is being measured at scales where quantum mechanics cannot be ignored. At every one of these frontiers, the same essential act is taking place. The universe is being asked a precise, specific question, in the most careful and controlled conditions that human ingenuity can create. And the universe, patient and exact as always, answers, sometimes in confirmation, sometimes in silence, and occasionally, in the ways that matter most, in surprise. The search continues. Quietly, methodically, one extraordinary measurement at a time. There is a place where two of the greatest intellectual achievements in human history meet, and fail to agree. On one side stands general relativity, Einstein's theory of gravity, a framework of breathtaking elegance that describes how mass and energy curve the fabric of space-time, and how that curvature determines the motion of everything from planets to light itself. On the other side stands quantum mechanics, the theory of the very small, governing the behavior of particles and fields at scales far below what any human sense can perceive. Each theory has been tested with extraordinary precision within its own domain. Each has never been found wrong in any experiment designed to probe it. And yet, at a deep mathematical level, they are incompatible. They rest on different foundations, make different assumptions about the nature of reality, and produce irreconcilable results when both are applied simultaneously to the same system. This is not a minor technical inconvenience. It is the central unresolved problem of fundamental physics. And it has been unresolved for nearly a century. General relativity describes gravity as a smooth, continuous curvature of space-time, a classical field that varies continuously in space and time, deterministic in its evolution, with no room for the probabilistic fuzziness of quantum mechanics. Quantum mechanics, by contrast, describes a world of discrete energy levels, probabilistic outcomes, and fields that fluctuate even in their ground states. When you try to apply the techniques of quantum field theory, the framework that successfully quantizes electromagnetism, the weak force, and the strong force, to gravity, the mathematics produces infinities that cannot be removed by the standard renormalization procedures that work for every other force. The theory becomes non-renormalizable, meaning it loses its predictive power at high energies. It breaks down precisely where it is most needed, at the Planck scale, near black hole singularities, at the moment of the Big Bang. String theory, one of the leading frameworks for addressing this problem, proposes that the fundamental objects of nature are not point particles but one-dimensional vibrating strings of energy, whose different vibrational modes appear as different particles. In string theory, gravity emerges naturally alongside the other forces, and the mathematics is free of the infinities that plague the point-particle approach. The framework requires extra spatial dimensions, typically 6 or 7 beyond the 3 we observe, curled up at scales far below anything we can detect. It also predicts supersymmetry. And it has generated an enormous amount of beautiful mathematics, some of which has found unexpected applications in condensed matter physics and pure mathematics entirely independently of whether the theory is correct as a description of nature. But it has not made a confirmed experimental prediction. It has not told us something we did not already know, in a way that an experiment could then verify. And without that, without the hard test of experimental confirmation, it remains a candidate, not a confirmed theory. Loop quantum gravity takes a different approach. Rather than replacing the point-particle framework entirely, it attempts to quantize spacetime itself, to make the geometry of space and time discrete at the Planck scale, built from finite, indivisible chunks of area and volume. It does not require extra dimensions or supersymmetry. It is more conservative in its assumptions, working directly with the structure of general relativity and applying quantum mechanical principles to it. But it too faces significant challenges, in particular, recovering the smooth spacetime of general relativity from the discrete quantum geometry at ordinary scales, and making contact with the physics of matter fields in a way that reproduces the standard model. Other approaches exist: causal dynamical triangulations, causal set theory, asymptotic safety, each taking a different path toward the same goal, each with its own mathematical character and its own set of challenges. None has achieved the status of an experimentally confirmed theory. The problem of quantum gravity remains, as it has for decades, genuinely open. Some physicists argue that the difficulty runs even deeper, that the problem is not merely technical, not simply a matter of finding the right mathematical framework, but that it reflects a genuine gap in our understanding of the foundations of quantum mechanics itself. Quantum mechanics, as it is currently used, is extraordinarily successful at predicting the outcomes of measurements. But its interpretation, what it actually says about the nature of reality between measurements, remains contested in a way that is unusual for a mature physical theory. The Copenhagen interpretation, dominant for most of the 20th century, essentially declines to say anything definite about what happens between measurements, treating the wave function as a calculational tool rather than a description of physical reality. The many worlds interpretation takes the wave function entirely seriously as a description of reality, concluding that all possible outcomes of every quantum measurement actually occur in branching, non-communicating copies of the universe. Pilot wave theory restores determinism by positing a real wave guiding real particles along definite trajectories. Relational quantum mechanics argues that quantum states are always relative to an observer. Cubism treats quantum mechanics as a theory about the beliefs of agents rather than about reality itself. These are not merely philosophical disputes. They have potential physical implications, particularly for quantum gravity, where the question of what an observer is and what a measurement means becomes deeply fraught when spacetime itself is subject to quantum fluctuations. Some theorists argue that a better understanding of quantum foundations, of what the theory actually means, not just how to use it, is a prerequisite for making progress on quantum gravity. That the two problems are linked, and that solving one may require solving the other. This is the deep theoretical landscape, two great frameworks in tension, surrounded by a galaxy of proposed solutions, each mathematically rich and experimentally elusive. It is a landscape that has occupied some of the finest scientific minds of the past century, and that continues to draw new generations of physicists whose careers may be devoted entirely to this challenge. And meanwhile, at a different frontier, not in the theoretical realm but in the laboratory, the quantum world is being explored and extended in ways that would have seemed fantastical even a decade ago. New states of matter are being discovered. New quantum phenomena are being observed and controlled. The boundary of what quantum mechanics can do, not just as a theoretical framework but as a practical tool for creating and manipulating physical systems, is advancing rapidly. Consider what has happened in just the past few years. Physicists have observed a phenomenon called self-induced superradiant masing in certain quantum systems, a process in which a collection of quantum emitters spontaneously synchronizes and emits coherent radiation without requiring an external cavity to sustain the oscillation. In conventional lasers and masers, the cavity, the arrangement of mirrors or boundaries that reflects the emitted radiation back and forth, plays an essential role in building up coherent emission. Superradiant masing occurs when the collective quantum behavior of the emitters themselves generates the coherence, without this external support. The observation of self-induced superradiance represents a new regime of quantum optical behavior, one in which the quantum correlations among many emitters produce effects that no single emitter could achieve alone. It points toward new possibilities for clocks, sensors, and coherent light sources of unusual stability. Time crystals are another recent addition to the catalog of quantum states that physics has learned to create and study. In ordinary matter, crystals are structures that break the continuous symmetry of space. They are not uniform in all directions, but have a repeating pattern at discrete intervals. A time crystal is the temporal analog, a system that breaks the continuous symmetry of time, oscillating at a period that is different from, specifically, a fraction of any external driving frequency, settling into a stable, persistent oscillation without absorbing net energy from its environment in the long run. Time crystals were first proposed theoretically in 2012, debated extensively as to whether they could be physically realized, and then observed experimentally in the years following, initially in systems of trapped ions and nitrogen vacancy centers in diamond, and subsequently using superconducting quantum processors. Laser-based implementations have extended this further, creating time crystalline behavior in optically driven systems with a degree of control and observability that opens new avenues for studying non-equilibrium quantum phases. What makes time crystals conceptually significant is that they represent a phase of matter in which the organizing principle is temporal rather than spatial, a system that finds its stable configuration not in the arrangement of particles in space but in the pattern of behavior in time. They demonstrate that the concept of spontaneous symmetry breaking, one of the central organizing ideas of condensed matter physics, extends into the time domain in ways that were not previously appreciated. And they exist only because of quantum coherence. Classical systems do not exhibit true time crystalline behavior. They are, in this sense, genuinely quantum states of matter with no classical counterpart. Fractional excitons are another example of the extraordinary richness that quantum mechanics makes possible in materials. An exciton is a bound state of an electron and the hole it leaves behind when it is excited, a kind of hydrogen atom made not of a proton and electron, but of an electron in its own absence, held together by electrostatic attraction. Excitons are familiar players in semiconductor physics and optoelectronics. But fractional excitons are something stranger. They carry fractional quantum numbers, fractional charge, or fractional statistics that lie between those of ordinary bosons and fermions. They are the excitonic analog of the fractional quantum Hall effect, in which strongly interacting electrons in two-dimensional systems under strong magnetic fields give rise to quasiparticles with fractional charges, bearing quantum statistics that are neither bosonic nor fermionic but something in between, what physicists call anionic statistics, named for the fact that they can be anything between the two familiar extremes. The observation of fractional excitons extends this exotic physics into new materials and contexts, suggesting that the fractional quantum Hall physics is not limited to the specific conditions under which it was first discovered, but is a more general phenomenon accessible in a broader class of quantum systems. These quasiparticles with unusual statistics are not merely curiosities. They are potential building blocks for topological quantum computing, an approach to quantum information processing that uses the global topological properties of quantum states to protect information from local perturbations and errors. This connection between quantum criticality and electronic topology is one of the most active and productive areas of condensed matter physics today. Topological insulators, topological superconductors, Weyl semimetals, topological Kondo insulators. These are materials whose electronic properties are determined not by the detailed local chemistry of their constituent atoms, but by global topological invariance of their quantum mechanical band structure. They are robust. Their characteristic properties are protected by topology in the same way that the number of holes in a surface is protected. You cannot change it by smooth deformations, only by tearing. In the context of electronic materials, this means that the surface states of topological insulators, for instance, are protected against scattering by ordinary impurities, because the topology of the band structure forbids the kind of backscattering that would normally occur. Strongly interacting electrons can create topological behavior of this kind in ways that are particularly rich, because when electrons interact strongly with each other, they can form correlated states in which the effective quasiparticles behave in ways that bear no simple resemblance to individual electrons. The fractional quantum Hall state is the paradigmatic example, but there are many others: spin liquids, non-Fermi liquids, strange metals, orbital selective Mott insulators. In each case, the collective quantum behavior of many strongly interacting electrons gives rise to emergent phenomena, properties that exist only because of the interactions, that cannot be understood by thinking about individual electrons in isolation, and that often exhibit topological character with potential technological implications. The technological implications are not hypothetical. Topological states of matter are among the most promising platforms for fault-tolerant quantum computing, the goal of building quantum computers that can perform reliable computations despite the inevitable presence of noise and errors in physical systems. Conventional approaches to quantum error correction require encoding logical qubits in large numbers of physical qubits, with the ratio becoming more favorable as error rates decrease. Topological quantum computing takes a different approach. It uses quasiparticles with non-abelian anionic statistics, whose quantum states are intrinsically protected from local errors by their topological nature. Performing a computation corresponds to braiding these quasiparticles around each other. The result depends only on the topology of the braid, not on the precise details of how it was executed. This makes the computation inherently robust in a way that no amount of engineering can replicate in conventional systems. Microsoft has invested heavily in this approach, pursuing a platform based on Majorana zero modes, exotic quantum states that appear at the boundaries of topological superconductors and that are their own antiparticles, related to the Majorana fermions we discussed in the context of neutrinos. Progress has been slow and the path technically arduous, but the potential payoff, quantum computing that is robust by virtue of its physics rather than its engineering, remains compelling. And the experimental progress in quantum states has not been limited to materials. Room temperature quantum devices, once largely considered out of reach for systems requiring quantum coherence, are being developed in new ways. A device using twisted light beams carrying orbital angular momentum, whose spatial mode structure is twisted in a helical pattern, has demonstrated quantum optical effects at room temperature in carefully engineered photonic systems. the ability to perform quantum operations without cryogenic cooling would be transformative for practical applications, and while full room temperature quantum computing remains distant, demonstrations of specific quantum effects and protocols at ambient temperatures are accumulating. In quantum information science, the ability to reliably generate and detect specific entangled states is a crucial capability. W states, a particular type of multi-particle entangled state in which the entanglement is distributed across all particles in a specific way that makes it robust against the loss of any single particle, have historically been difficult to detect and verify efficiently. Recent experimental work has demonstrated methods for instantly detecting W states using optimized measurement protocols, reducing the overhead of state verification in quantum networks and quantum communication systems. Each advance of this kind, though it may seem narrow and technical, is a building block for the larger architecture of quantum technology. The sensitivity of quantum sensors has reached levels that seem almost impossible to state in familiar terms. Sensors capable of detecting energies below a zeptajoule, that is, below 10 to the negative 21st joules, have been demonstrated using superconducting circuits and other quantum platforms. A zeptajoule is a billionth of a trillionth of a joule. To put that in some kind of perspective, a single photon of visible light carries an energy of roughly a few hundred zeptajoules. These sensors are detecting energy transfers at a scale that begins to approach single quantum sensitivity. Applications range from dark matter detection, searching for the extraordinarily faint signals that hypothetical dark matter particles would produce when interacting with a detector, to medical imaging, to fundamental measurements in quantum thermodynamics. The intersection of quantum physics with artificial intelligence and machine learning is also opening new possibilities that would have been difficult to anticipate. Transfer learning, a machine learning technique in which a model trained on one task is adapted to perform a related but different task, is being applied to particle physics data analysis in ways that dramatically accelerate the search for new physics. Rather than training a new model from scratch for each new experimental signature, transfer learning allows knowledge gained from simulations or from analyzing one type of signal to be rapidly applied to searching for different signals. This reduces the computational cost and time required to scan vast datasets for rare events, effectively extending the reach of experiments without requiring additional running time or new apparatus. In condensed matter physics, a new quantum liquid crystal state has been observed, a phase of matter that combines the orientational order of a crystal with the absence of long-range positional order characteristic of a liquid, but in which these properties are governed by quantum mechanics rather than classical thermodynamics. Quantum liquid crystals exist near quantum phase transitions, the zero-temperature analog of classical phase transitions, driven by quantum fluctuations rather than thermal ones, and their properties are intimately connected to the strange metallic behavior observed in high-temperature superconductors and other strongly correlated electron systems. Understanding quantum liquid crystals may be a key step toward understanding why certain materials become superconducting at temperatures far higher than conventional theory predicts, one of the outstanding unsolved problems in condensed matter physics with potentially enormous practical implications. Repulsively bound magnons represent another unexpected quantum phenomenon. Magnons are quasiparticles representing collective spin excitations in magnetic materials, the quantum of spin waves, analogous to the way phonons are quanta of lattice vibrations. Normally, one might expect that repulsive interactions between magnons would cause them to fly apart. But in certain quantum systems, repulsive interactions can actually bind quasiparticles together, creating bound states that are stabilized by the repulsion rather than by attraction, a quantum mechanical effect with no classical analog. The observation of repulsively bound magnons in controlled quantum systems, including implementations using ultracold atoms and optical lattices, where interactions can be tuned with great precision, demonstrates once again how quantum mechanics produces behavior that directly contradicts classical intuition, and suggests new possibilities for engineering exotic quantum states with specific properties. Each of these discoveries, time crystals, fractional excitons, quantum liquid crystals, repulsively bound magnons, room temperature quantum devices, zeptigal sensors, is a piece of a larger picture that is still being assembled. Individually, each represents a new phenomenon, a new state of matter, a new capability. Together, they are evidence of a field in extraordinary ferment, discovering new quantum phases and new quantum effects at a rate that accelerates as experimental tools improve and theoretical understanding deepens. The future of quantum technology is already arriving, incrementally, in laboratories around the world. Quantum computers with increasing numbers of qubits and decreasing error rates. Quantum networks transmitting entangled states over growing distances. Quantum sensors of sensitivity that continues to approach and in some cases reach the fundamental limits set by quantum mechanics itself. These are not distant possibilities. They are present realities at various stages of development, from early demonstrations to more mature platforms approaching practical utility. And at the frontier of fundamental physics, the major experiments of the coming decades promise discoveries that could reshape our understanding of the universe as profoundly as any in the past century. The next generation of neutrino experiments, DUNE, Hypercameo-Candy, will probe CP violation in the neutrino sector with unprecedented sensitivity, potentially revealing whether neutrinos behave differently from antineutrinos in ways that could explain the matter-antimatter asymmetry of the universe. The ton-scale neutrinoless double beta decay experiments will determine whether neutrinos are their own antiparticles, settling one of the deepest open questions about the nature of matter. Dark matter experiments will either detect the particles making up the invisible majority of the universe's mass, or rule out the most well-motivated candidates and force a fundamental rethinking of what dark matter is. At the LHC, the high luminosity upgrade, increasing the collision rate by roughly a factor of 10 compared to the current configuration, will produce an enormous dataset that will allow precision tests of standard model predictions at a level never before achieved, and that will either uncover the subtle signatures of new physics in rare processes, or place constraints so stringent that entire classes of beyond the standard model theories are definitively ruled out. Future colliders, the Future Circular Collider at CERN, the International Linear Collider in Japan, and other proposals, would push to energy scales significantly beyond the LHC, potentially producing new particles directly if they exist at those energies. Decisions about which, if any, of these facilities to build are among the most consequential in the planning of fundamental science for the coming decades. In gravitational wave astronomy, the LIGO and Virgo detectors have already opened an entirely new observational window on the universe, detecting the space-time ripples produced by merging black holes and neutron stars. Future ground-based detectors, the Einstein Telescope in Europe, Cosmic Explorer in the United States, will be dramatically more sensitive, capable of detecting gravitational wave sources across the entire observable universe and probing the equation of state of neutron star matter with unprecedented precision. The space-based LISA mission, currently in development, will detect gravitational waves at much lower frequencies than ground-based detectors can access, opening the possibility of observing supermassive black hole mergers, compact binary systems throughout the galaxy, and potentially gravitational wave backgrounds from the early universe, including, possibly, signals from the inflationary era. If a gravitational wave background from inflation is detected, it would provide direct observational evidence for physics at energy scales close to the Planck scale, the regime where quantum gravity is relevant. It would be the closest thing to a direct probe of the quantum nature of spacetime that observation is likely to afford in the foreseeable future. And it would constrain, potentially decisively, the space of viable inflationary models, pointing toward a specific class of theories and away from others. The universe, examined from all these directions simultaneously, with particle accelerators and underground detectors and quantum sensors and gravitational wave observatories and precision measurements of ordinary atoms, is being asked the same set of deep questions from many different angles at once. What is the nature of dark matter and dark energy? Why does more matter than antimatter exist? What lies beyond the Standard Model? What is the quantum nature of gravity? Are neutrinos their own antiparticles? Does the proton decay? These questions have resisted answers for decades. But the tools being brought to bear on them now are more powerful than they have ever been. And the history of physics gives some reason for quiet confidence that the universe, examined with enough care and precision and ingenuity, will eventually yield its answers. Perhaps not all of them at once. Perhaps not in the ways we currently expect. The history of physics is full of discoveries that arrived from unexpected directions, that required abandoning assumptions that had seemed secure, that revealed a reality stranger and richer than any prior framework had anticipated. The next great discoveries may follow the same pattern, emerging from an anomaly that does not fit, from a measurement that refuses to agree with theory, from a phenomenon observed in a new material or a new energy regime that opens an entirely new chapter. What we can say, with some confidence, is that we are at a genuinely extraordinary moment. The Standard Model is complete and simultaneously insufficient. Quantum mechanics is more precisely verified than any other theory in science, and simultaneously mysterious in its foundations. General relativity describes the universe on the largest scales with breathtaking accuracy, and cannot be reconciled with quantum mechanics at the smallest. New quantum states are being discovered and controlled at a pace that would astonish the physicists of a generation ago. And the questions that remain unanswered are not peripheral questions, not details to be tidied up at the margins. They are central. They concern the nature of 95% of the universe, the origin of all matter, the ultimate fate of every atom, and the deepest structure of space and time. The atoms that make up your body, forged in ancient stars, assembled by the quiet processes of chemistry and biology over billions of years, are themselves expressions of the quantum world we have been exploring throughout this journey. The quarks bound by gluons inside the protons of your cells. The electrons whose quantum mechanical behavior determines every chemical bond, every nerve signal, every breath. The neutrinos streaming through you from a sun 93 million miles away. All of it governed by the same equations, the same quantum fields, the same fundamental forces that physicists are still working to fully understand. The science of the very small turns out to be the science of everything. The journey into the atom does not lead away from the world of ordinary experience, it leads deeper into the foundations that make that experience possible. Every texture, every color, every thought, every heartbeat, all of it assembled from quantum fields and probability and the extraordinary richness of a universe that seems, the more carefully we look, to be endlessly more interesting than we had previously imagined. And somewhere in the quiet running of experiments, in the patient accumulation of data, in the late nights of calculation and the long days of building and testing and calibrating, somewhere in all of that human effort, the next revelation is forming. Not yet visible, not yet named, but there, waiting, in the deep structure of a universe that has never, in all of history, run out of new things to say.